Yeah. Okay, cool. Yeah, nice to meet you. Yeah, good to go. Yeah. Okay, so I'll be doing a workshop on Shinigami. I'll start with kind of explaining what it is, and then I'll go into the basics of like what script is, and then see where we go from there. So Shinigami is pretty much a start client for Bitcoin, or it's a set of start tools to be used for scaling Bitcoin in different ways. So essentially, the Starkware team's kind of goal in general with Shinigami and exploration projects that we're working on is scaling Bitcoin with and without soft forks, figuring out all the different ways that we can use Starks to help Bitcoin reach mass scale. So that's where Shinigami comes into play. So Shinigami is a set of libraries written in Cairo to allow us to use the power of Starks to superpower Bitcoin. And since we're using Cairo, it allows us to be natively provable, and I'll kind of go into what that means in a bit. But Shinigami is kind of split into two different parts. There's the execution and consensus libraries. The consensus library can also be referred to as Rito, so y'all might hear that name floating around. But I will be mainly focusing on the execution part because that's what I've worked on, but I'll go into the consensus part as well. So Shinigami execution. So what Shinigami execution library is it's a Bitcoin execution engine written in Cairo. So essentially what that would mean is that we want to execute Bitcoin script in a way that we can create start proofs of that execution, which would allow us to run super fast. So if you're not familiar with Bitcoin script, I'll kind of go into some basic examples. So a lot of people aren't familiar with the fact that Bitcoin actually does have a scripting language. It's basically just like an assembly language that has a handful of opcodes, I think around like 150, depending on how you count them. And this is a very, very basic example where we're just adding some numbers together and comparing that they're equal. So we start with op2, which will push 2 onto the stack. So Bitcoin script is a stack-based language, so every opcode interacts with the stack. So op2 will push 2 onto the stack, op3 will push 3, and then op-add will take those two numbers off the stack, add them together, and then put the results back onto the stack. So we end up with 5. Op5 will push 5 onto the stack, and then op-equal checks that the two values on the stack are equal, and if they are, it'll push a 1 onto the stack. Since 5 is equal to 5, we get 1. And at the end of a Bitcoin script execution, we check the stack, and if at the top of the stack it is a 0, then the script is invalid, and otherwise it is spendable. And since 5 was equal to 5, we know that this transaction would be spendable. Not a super useful script because anybody could probably figure out that 5 equals 5 and then spend your Bitcoin. So let's kind of go into a more realistic example of how Bitcoin transaction execution would work. So how the Bitcoin state is laid out, essentially there's a bunch of UTXOs. It means unspent transaction outputs. So these are all different Bitcoins that people own, and they're nested in these UTXOs. So let's say you want to spend UTXO-6, which has like 3 Bitcoin in it. So there will be some locking script associated with the UTXO. I'll be doing a very simple, it's probably the most simple kind of locking script that's on Bitcoin mainnet now, is a pay to public key. It essentially consists of 2 opcodes. So the first is an opcode that pushes the owner's public key onto the stack. So if you own UTXO-6 and you want to be able to spend it, then you should have the private key that links to this public key in the locking script. And then the last opcode is op-check-sig, and we'll go into that. And let's say you want to spend this UTXO-6, say you'll pass this transaction or you'll send this transaction to the Bitcoin network, which consists of the inputs and the outputs. So the input would be UTXO-6, a reference to the UTXO that's in the Bitcoin state. An unlocking script, you'll give the unlocking script, which is a separate Bitcoin script from the locking script that's in the UTXO that is used to unlock the Bitcoin. And you'll give a new set of outputs, which will be a new set of UTXOs that you want to put into the state. Say, if it's another pay to public key, you'll have another UTXO with somebody else's public key in there so they can spend the Bitcoin whenever they're ready. So let's kind of go into the flow of how this transaction executes through the Bitcoin engine and also the Shinigami engine. So we start with the unlocking script, first executes. The unlocking script for a simple pay to public key is just the signed transaction data. So it'll just push the signed transaction data to the stack, and then it's done. It's done with the unlocking script. And then UTXO-6 will execute. We kind of went over what the script was there. So first, it pushes the owner's public key onto the stack, and then opcheck_sig executes, which is a pretty complicated opcode, but I'll make it a little bit easier, hopefully. So essentially what opcheck_sig does is it takes the signed transaction and owner's public key off the stack. It checks that this public key can, in fact, decode this transaction, meaning that the owner signed the transaction properly with their private key that's linked to this public key. And if it was, in fact, a valid signature, then we say, hey, we push 1 onto the stack. If it wasn't a valid signature, we would push a 0. And like I said at the beginning, since there's a 1 on the stack at the end of the script execution, we know that this transaction is valid. So this new UTXO can go into the state, and the old UTXO-6 will be removed from the state because it was spent. And this new UTXO will be linked to whoever you sent the money to. Bitcoin has like the ability to have arbitrarily large, or not arbitrarily large, but very large transactions with a bunch of different inputs and a bunch of different outputs. This simple example that I went through is just 1 input, 1 output. But you could imagine having like 100 different inputs, and each input you'll pass an unlocking script in your transaction and provide as many outputs as you want depending on who you're sending the money to, or if you want to send certain parts of the money back to yourself and so on. I put a couple examples of some large transactions on the Bitcoin network. I think one of the largest transactions at the beginning of the Bitcoin's lifetime was the infamous or famous, I guess, 10,000 Bitcoin pizza, where somebody spent 10,000 Bitcoins to buy a pizza on the mainnet. It had like 130 inputs, so it was a relatively large transaction. You can imagine more complex computational transactions like a 20 of 20 multisig, where you need 20 people to sign the transaction and pass their data or pass their signatures to the transaction to be able to spend. And a recent development that's, I imagine, will be a super large script if it's ever implemented on mainnet is something called Collider script, which is essentially a script that will allow people to do covenants, or it seems like it would allow people to do covenants on Bitcoin today, but it requires like a SHA-1 and a RIP-EMD implementation in script. So if you were to implement those in script, the transaction will be massive when you're spending. So yeah, I also put the limit for Bitcoin transactions on mainnet. The theoretical limit for a transaction size is about 4 megabytes. So each opcode that executes is about 1 byte, or it is 1 byte, but if you do like push data opcodes, you can have more. So you could have like 4 megabytes worth of opcodes in any transaction, and all of those would need to execute one after another. So it could be pretty computationally intensive. So that's where Shinigami comes in. I'll kind of briefly discuss Cairo here. So Cairo is a Rust-like Turing-complete programming language developed by the Starkware team. It allows you to easily create provable programs in like a normal programming way, like instead of having to build like custom circuits or do anything crazy like that. You just program like you normally would, and by the nature of building in Cairo, you're able to execute those programs in a provable context. And Cairo's been used a lot for StarkNet and things like StarkX exchanges, so it seems to be pretty battle tested at the current state. So those are some pros of using Cairo, which is why we built the Shinigami engine in Cairo, which will allow us to compress we can compress a lot more transactions than the 4 megabyte limit into a 4 megabyte proof to post onto Bitcoin or any other chain that we want to prove the transactions on. So now I'll kind of go into the coding section, or like go over the code of the Shinigami engine. So this is a bit of a reduced version of how the Shinigami engine works. It makes it easier to fit on a slide and easier to look at. So essentially, when we want to execute the transaction, we first loop over each of the scripts. Like I discussed, those are like the unlocking script and the locking script. And if you have like witness or anything like that, or newer Bitcoin types of transactions, you execute those as well, and you loop through them. And then for each script, you just loop over all the opcodes, all the different types of opcodes like push data, manipulating data, doing hashes, signature checks, and things like that. And then for each opcode, we execute it through the Cairo program. And then at the very end of the script executions, we check if it's valid, if there's like a 0 or a 1 at the top of the stack. And if it is, we know that it's a valid transaction. So like I mentioned, each transaction can have multiple different types of inputs or multiple different inputs. So this is the function that we use in the Shinigami engine to validate transactions. So we loop through each of the inputs or the UTXOs to spend. We create an engine instance with the transactions data and the public key, or like the unlocking script, and we execute the script and check the results. And if there was no errors, we know that the transaction was spendable, so it is a valid transaction. Otherwise, we return an error, and the caller can indicate that to the proof that it is not a valid transaction. So I will go through a basic example transaction through the Shinigami engine. Here, this is the very first ever transaction from Satoshi to Helfini. I'll kind of explain it a bit. I want to look at the details. So this is the transactional mempool.space. It's like one of the famous Bitcoin block explorers. But essentially, this is the transaction here. So you can see the script sig, which is what I called the unlocking script. Yeah. So the script sig is the unlocking script that is passed with the UTXO. So you can see here that it pushes, it is passed by the transaction. We can see it's just one simple opcode that pushes the signed transaction data to the stack. And then the previous output script, this is from the UTXO. We can see it just does one push data opcode that pushes the public key. So this is the public key from the spender. You can see here that it's the same as the public key that was sent to, and we do the op check sig. So it's a very simple pay to public key transaction. And here is the same transaction on something called Learn Me Bitcoin. I just wanted to show this one thing. Essentially, this is the transaction data. So all of this is just like a bunch of numbers. You can't really read it, but if you were to like look at individual parts, you can see that this is the input that the user provides from the UTXO. So this is like a reference to the UTXO in state here based on the transaction ID and like which output it was. And then this is the unlocking script that the user passes with their transaction. And it is all stored like in this raw transaction data that the user passes to the Bitcoin network. And then at the end, we have like the outputs that we want to pass to the new Bitcoin state so people can spend the transaction in the future, or spend the UTXO in the future, I should say. Okay. So what I just showed on Learn Me Bitcoin is like all this raw transaction data. And what we do first in the Shinigami engine, or like to test the Shinigami engine, is we deserialize that data into a transaction type, which consists of like the inputs, the unlocking scripts, and the outputs. We set up the Bitcoin state, or the assumed Bitcoin state here with just the locking script and the UTXOs. And there's only one UTXO being spent here, so we only really need to set up one. And then we validate the transaction with that function I showed earlier. So this is the basic flow of creating a proof from a Bitcoin transaction. The user provides the transactions that they want to prove. They provide the UTXOs that are in the Bitcoin state to Shinigami. Shinigami runs the Bitcoin transactions through something called the Cairo VM, which allows you to get a trace of the program's execution. And with that trace, you can pass it to a prover. Our prover that we hope to be using in the future is called Stew, which allows you to compress the transactions trace. You can think about it as compressing the transactions trace into a Stark proof that is super efficient to be verified. So the prover provides this proof to you, and then you can pass the proof to any verifier anywhere. So it could be on Bitcoin if we have a Bitcoin Stark verifier. It could be on Ethereum Starknet. It could even be like on your phone or something. You just run the proof, which is a much more succinct, short calculation than running all of the transactions on your own. And if you were vigilant, you might have noticed that I passed this UTXO as an input from the user for the Shinigami engine. And I could have just put anything here. So anybody could have just put an arbitrary UTXO that doesn't actually exist in the state, and then created a proof that that transaction was valid even though it technically wouldn't have been, because the UTXO doesn't exist on Bitcoin. So how do we track that users provide valid UTXOs? And that's where Shinigami consensus kind of comes in. So we have the separate library called Rito that does Shinigami consensus management, which includes the state management. So that would be where you store all the UTXOs that are considered to be valid. And you we use something called UTXO. The best way to think about it is you can think of it as like a giant Merkle tree containing all of the UTXOs that are valid. And then anytime you want to spend a UTXO, you provide a Merkle proof of the UTXOs that you spend, and then you recursively verify, or you also have to recursively verify that the UTXOs are valid previously from, sorry.
So I'm familiar with UTXO, which is pretty cool, but are you using that because these Stark proofs are, like, they don't like big memory things? Because the whole UTXO set is 10 gigabytes. The UTXO, sorry, just so we can get that. Oh, I was saying I'm familiar with UTXO. It really compresses the whole UTXO set in a few kilobytes. Are you using it because you don't want to deal with 10 gigabyte things inside your Stark proofs, or is it useful for some other mathematical reason?
That's exactly right. So we want to provide as little, or we want the Stark proof to have as little memory as possible, because the more large the amount of memory that we need is, the larger the trace and the larger the amount of time needed to prove. So yeah, you're exactly right. That's why. Shinigami consensus also does things that you might have heard from a previous project called ZeroSync, where it does difficulty checks, ensuring that Coinbase transactions are valid, and things like that. So you can ensure that the Bitcoin consensus rules are followed properly through a Stark proof. And this is kind of like an image of how that works. So essentially what you do to validate blocks in through, you see my cursor? Okay. To verify blocks in through M, or to prove blocks in through M, is you provide a proof of the entire Bitcoin state up to n-1. And this is kind of like induction, if you're familiar with that from math class. But essentially you verify that the proof from 0 to n-1 is valid. And if you do that, then you ensure that you have the correct chain state. And using UTXO proofs and the block data from N to M, you can provide that to the Shinigami consensus library and then create a new proof of from 0 to M, up to M. And then you'll just continually do this every time you want to create a new section or a new proof to post to a bridge or whatever use case you're using, which is what I'll go into now. So how much time do I have? So the essential idea of Shinigami, some of the use cases for Shinigami include initial block downloads. So when you start a Bitcoin full node, you have to essentially run all the Bitcoin transactions from Genesis up to the current state. Otherwise, you don't really know for sure if the state that you were passed by the network is valid. And with a proof, if you create a proof like this of blocks 0 all the way up to the current head, you can verify that proof. You'll know that all the consensus rules were followed, all the execution rules were followed, and that the latest state does in fact correspond with what is on Bitcoin mainnet. So you could do super fast and secure initial block downloads, start up your full nodes. We don't really have an estimate of how long it would take, but it would be logarithmically faster in theory. You could also do things like ZK clients nested in chains to do things like bridging. So this is kind of like a diagram explaining that. You get the same Stark proof proving the entire state of the Bitcoin chain. You pass it to an on-chain Stark verifier. And then the L2, L1, or whatever other protocol you're using verifies the proof. They'll know that the latest state is valid, and they can update the bridge's state so people can interact with the Bitcoin on the other layers. These two use cases were without FCAT or any changes to Bitcoin Core. I also wanted to put a couple use cases that I think would be interesting if we had things like FCAT, optimistic Stark verifiers, or like if you were just doing it on a separate network that had the ability to create Stark verifiers. And those are Bitcoin-like rollups and something that I'm calling Bitcoin threads. It's also been termed ZK threads by some people at the Starkware team. Essentially, the Bitcoin-like rollups is just like how EVM rollups work in a way. If you're familiar, you essentially just replicate how Bitcoin works in your own layer 2 or your own chain, and then you prove that chain state, and you can post the proofs to the Bitcoin. If you're using FCAT or some optimistic Stark verifier, you could act like this other layer 1 in this image is just Bitcoin, and then you can update your bridge. And then the idea behind Bitcoin threads is very similar. You could imagine spinning off a Bitcoin UTXO that is set up with a Stark verifier, and you could run as much arbitrary computation or Bitcoin-like computation off-chain, and then whenever you're ready to post back to Bitcoin and you're ready to use the Bitcoin network again, you just post the proof to Bitcoin. The verifier verifies that the proof is valid, and then it updates the UTXO outputs with that. So it just kind of runs as its own thread in a way, separate from the network. And yeah, so the project's fully open source. We actually pay people that do contributions. So if you're interested in the project or you want to contribute or just like look around, this is a link to the GitHub. And if I have time, I can go into the code.
You got like 5 minutes for questions.
Yeah, that's good too.
Questions, comments. Where'd you come up with the name Shinigami?
Sorry?
Where does the name Shinigami come from?
So most of our exploration team projects are like named after anime characters. So yeah, it's from Death Note. It's the god of death in Death Note, yeah.
I'll let you guys pass it on.
This might be a dumb question, but you know, I'm not as technically inclined, but let me just lay it out. Like the mid 90s, you had Sun Microsystem and what that did for the internet. What I'm trying to understand is like what you guys are providing, what customer pain are you solving? How many other people, what are the alternatives that people could use instead of Starkware? And how do you monetize? Is it, or is it just open source and all that? Obviously, I'm asking from an investor perspective here.
So the project itself is not really set up to be used by or to make money, I should say. It's more of like a public good project. It could be used by things that are more money focused. Like for instance, I think the biggest thing that we want it for at Starkware is the Bitcoin bridge. So we want to be able to bridge from Bitcoin to Starknet. And to do that, we have to be able to verify that Bitcoin state is valid on Starknet. So if we are able to create the proofs using Shinigami, we can do that. I hope that answered your question.
Thank you. So I guess kind of follow up on that. Earlier you had the Shinigami consensus. Is there any kind of, looking at it again from like an investor perspective, using that as some kind of way to like validate UTXOs and kind of using that in some way, or do you envision bringing all of these together? Kind of. I guess the question is, the origins of Shinigami consensus, and then where you guys want to take that.
So I think maybe also following or continuing what he was asking as well. So Shinigami consensus, mainly the main origin is from something that ZeroSync was doing. They were doing it to build these dark proofs for bridging and just like use cases around that field. But also Shinigami consensus can be used to do what I was discussing, like the rollups. So you can imagine a lot of Bitcoiners, they like the idea of Bitcoin. They want their money to be just used through Bitcoin's spec, only for spending, not really doing things like AMMs or NFTs or anything like that. So you can imagine if like you're an investor creating some kind of roll-up that's like Bitcoin, and you could pitch that to more Bitcoin maxi people, or like just people that are more interested in how Bitcoin works and only doing transactions. And you'll be able to process a lot faster and still be decentralized without relying on like optimistic rollups and things like that. You could just create proofs of a giant chain and yeah, if that makes sense.
So just to confirm, with Shinigami, we're not restricted to Bitcoin-like functionality inside the rollup itself.
Did you say that again? Sorry.
So we have obviously Bitcoin script. You're not restricted to primitives or scripts that you could create in that. You're able to do a rollup of anything in a more Rust-like manner.
It would still be a rollup of Bitcoin script execution. So it would be just like Bitcoin. You wouldn't be able to do like Rust programs, for instance, if that's what you were saying. But technically you could extend Bitcoin's functionality through Shinigami and it would still be provable. Like for instance, if you wanted to activate FCAT on your own Bitcoin rollup, you could still do that with Shinigami. I mean, not currently, but it's possible to do it with Shinigami, and you'd be able to create those Stark proofs in the same way. Does that make sense? Yeah.
Yeah, I appreciate that.
Yes, so my understanding, if you want to do some, computation on blockchains is very expensive. If you want to go do it somewhere cheaper and create a proof and then just put that proof on chain, that's a lot cheaper to do. But my question is, what is the feasibility for an average user to be creating proofs? Because those are pretty computationally intensive. So even though you're doing it in a cheaper environment, like what does the cost look like if I'm a user and I want to create proofs of Bitcoin-like execution to post on chain?
Yeah. So in the current state, creating proofs is not very friendly for end users. Like, I'll give an example. So StarkNet itself has its own prover, and Starkware runs the prover. And it is very large. I don't know the exact specs, but I imagine it's somewhere around like 500 gigabytes of RAM, which no user, I don't imagine anybody in this room has that much on their computer. He does back there. But with the development, we're developing something called Stew now, which is, we don't know the numbers exactly because it's still in development, but we expect it to be a lot more friendly for end users to be able to do what we call client-side proving, where you can create proofs on your phone or on your laptop. Creating proofs of Shinigami execution in particular, though, with Stew, I'm personally doubtful that it will still be friendly for end users, just because Bitcoin transactions are so large, the transaction execution context can be massive. So yeah, it's the good thing about provers, though, or like creating Stark proofs, is that only one person needs to run the prover. One person creates the proof, and once it's done, anybody can verify it, and it's very, very efficient to be verified. That's the purpose of it. So while it would be really good to have proving be commercially available or like be available to end users, it's not a deal breaker for most use cases at the current moment. Yeah.
Thank you.
Hey, thanks, Brandon.
Yeah, thank you.
Rock on. We're going to chill here and let that room end, and then Mike Casey and Portland will come over here, talk about Enduro, probably some cool demos, and over there is Peter Todd doing his layer to covenant review, right? Whatever, it's the covenant-dependent layer 2 review. So Enduro here, as soon as we see Mike in Portland, and Peter over there as soon as it wraps up. So yeah, hang out, go grab a coffee, chill. Thanks.
Coffee is nice on the 14th floor, right?
There's lattes on the...
Nice.
I have a question. Where does the name Enduro come from?
Oh, okay. Well, that was like a workshop thing. Actually, a lot of people compare it to a male supplement, but it was actually no. It was a name that I was workshopping with Julian Duran, and it actually did come from. Because it was Marathon was launching a sidechain platform, and it was originally, okay, well, what do you play on Marathon? And it was like, well, endurance, and like Enduro, and I was like, that doesn't sound right. And we just said, well, what about Anduro? And it works pretty well because you can kind of say it in any language. It kind of fits anywhere, and it doesn't really mean anything. So that's the genesis of that.
Cool. I've been wanting to ask that question for a while.
We get a lot of choice comments about it, but it's a decent name. No, I just had to boot. Routed on the podium. All right, let me. All right, well, thank you very much. I'm going to give the very, very, very high level of this. This is normally like a 35-minute presentation I do on this, but we only have 30 minutes, and we're doing a demo. So I got about 2 minutes here before Reese comes on, and we actually run through the demo. Let me explain really, really quickly about the Enduro platform. Enduro is actually a sidechain platform with associated apps that we're building out for the various sidechains. We have two sidechains currently on testnet, and Coordinate is the one that we're going to demo for you today and run a little workshop on. And Coordinate is a fork of Bitcoin Core, and it is Bitcoin Core. The whole idea of it is, let's say Bitcoin becomes this data layer, data availability layer for L2s. That's all you use it for. Well, I would still like to transact on Bitcoin using Bitcoin transactions. Where do you do that? Well, Coordinate's a good place to do that. And it does what Bitcoin does currently and a whole bunch more with an actual Bitcoin denominated token. And you can run native UTXO tokens on top of it. Plus, it uses hybrid consensus, which all Enduro sidechains operate on hybrid consensus between a strong federation and, of course, Bitcoin merge mining. So no shitcoin and pays the miners. Check both those boxes. So
Do you have like a QR code for your Twitter page?
I did at some point, but it's gone. All right, so really quick with coordinate. Yeah, basically the stuff I said here, UTXO-based, backward compatible, it's script, it's Bitcoin. Basically, it's Bitcoin. Anything Bitcoin does now, you can do on it. You can do Lightning, anything, and we want to keep feature parity with Bitcoin, so any soft forks that go through, you should be able to do. I don't know if we're going to activate FCAT. Several other chains have, and I don't know if it matters. It also supports assets, which we're going to go through in the demo here. So these are importantly native UTXO assets. So it's not like assets that you see on Bitcoin today. The name coordinate is like kind of a play on ordinals. It works along with, but it's not actually ordinal technology. We're not tracking individual sats here. What we do is we actually create these alternative assets as UTXOs themselves, which are respected by the actual consensus of the chain itself. So it's not this indexed meta layer. It's actually on a Bitcoin level, this is where these assets are moving. So the easiest way I've found to describe it is you have a UTXO set, and then the UTXO set has it has an extra field in it that says which asset you're talking about for this UTXO. That's basically at a high level what we did. The other thing, and there's a whole lot of crud in here, but the other thing we did is mine blocks and sign blocks and reorg resistance. Reorg resistance, the federation, it signs 3 blocks prior for a coordinate. So you have to include the commitment of the federation. So you can never have a chain fork over 3 blocks. It cannot happen. And then it has 2 types of transactions between sign blocks, which are MEV resistant through emergent consensus. So you're using public consensus to do it. Every node verifies their own order that they see things in. So if you were cheating out the order, it's first come, first serve for the transactions. If you're cheating out, it's very transparent and obvious that that's what's going on. So, and also premium transactions, which, yeah. So you never overpay for one of these transactions. They go, and it's either final or killed in about a minute. And there's no RBF bumping because it uses a reverse auction. It's pretty cool. So the goal is, hey, cheap Bitcoin again, bring it back to 2013, and oh yeah, add assets too. Sure, cool. All right, so that's the extremely fast version of this. So thank you very much. Reese, you want to get started with the? Yeah, sure. You got HDMI?
Go plug in, let me know.
You got those things.
Yeah, do.
All right, who all wants to participate? All right, so here's your work. There, list of C words.
These are the ones you're going to use.
Oh,
These
whoops.
will actively have CBTC.
All right,
the rest
fine.
are the rest are kind of a random grab bag.
Thank you.
Got a better word this time.
Yeah, better word. Some of these are actually kind of salacious. That's a fuse in here. There. Well, yeah, there's a alcohol. There you go. Thanks. Who else?
You don't know black this using.
I'm sure. Abuse, alcohol.
It would take some effort, but I feel like you do it.
Just the hits. Yeah, right.
Should I get my laptop after?
Yeah, you should if you would like to participate. So there are a couple of notes that to go through the full demo, you will need.
We actually went through all the slips, Reese.
Did you have any extras or were you short?
No, I gave what they were. It's cool.
Okay, great. Okay, awesome. So yeah, to kind of complete this demo, you'll need a laptop, the latest version of Python, Chrome or Chromium. Some people say Brave works with this. And then you will need to install the Chrome browser extension wallet. So just letting you know that to get through this whole thing, you must install this little browser wallet. You can uninstall, use like a just regular instance, and you can just remove it after you're done if you don't want.
Hello. Just a plug too. The Enduro wallets are also available for iOS and Play Store, App Store and Play Store. You can just search for Enduro and
then
download the wallet there as well. But we'll be doing primarily on the browser-based extension on
And we
Chrome.
built this at Marathon as well, so,
Yeah.
yeah. One second. Do you still have your laptop with all the assets to distribute? Oh, shit. Okay, we'll see here in a second. Okay, so kind of the first step to all this is that I'm going to assume that you already have Python installed and you have Chrome and Chromium, but you'll need to get the browser extension wallet. There we go. And this basically is used as kind of an introduction to being able to send and receive coordinate Bitcoin, coordinate testnet Bitcoin in this case, and coordinate assets through what we're going to work with today is the actual RPC. So I've created like a set of scripts that we can use to interact with a coordinate node that I'm hosting myself at my own location, but to make it easy so everybody can run with the same code and do things without having to set up the entire node, download, create wallets, etc. I've kind of already preloaded wallets in a little interesting way that hopefully is pretty easy to interact with. So from here, the initial thing with the wallet is you have a bunch of different little notifications. I'm going to see if I can fix one thing real quick with my setup. I think the scaling's off and it is far too big. Oh yeah, I literally had it. I was going to search, so let's go to 150. That should make things look a little bit more appropriately sized. Okay, perfect. Yeah, so once you get the wallet, basically it's going to ask you a bunch of questions like typical wallet setup, seed phrase, etc. But in this case, this is completely disposable to me, so we're just going to go with a brand new account. Portland HODL. It's going to give me a seed phrase, but since this is all testnet Bitcoin, has no value anyways, I'm just going to continue. Confirm your backup. I'm going to skip on that. And no thanks, I don't want to review. And let's not even set a password for this. Okay, so next is here. I have absolutely nothing in this wallet, brand new wallet. And this web wallet connects to a general just RPC server or indexer that essentially grabs the assets, is able to display the asset images, quantities, and balances. So this is not like you're connecting to your own self-hosted node or anything. It's just using another general public node. So in terms of the actual demo itself, we are going to need to run some Python. So let's clone the repository. By the way, anybody that's following along, you'll probably need to go to the Bitcoin repository or the coordinate repository here. So that's going to be at github.com/russaree. You should be able to go to RUSSEREE. I apologize for not using Portland HODL. That's a long-term holdover. And then in the repositories section, you'll have coordinate workshop. By the way, did anybody have trouble getting a hold of the web wallet? Okay. So once you get to the, has everybody gotten to the repository that wants to get there? Okay, perfect. We're going to clone this into our own local directory. So we're going to, I have my own Git directory, but I'm going to remove my existing copy. So we'll be all working together on this. So if there are bugs, I will see them too. So git clone. Okay. So, by the way, does anybody have a question on how to clone the repository onto their local machine? No? Okay, we're good to go. So to start interacting with these scripts, we're going to go into the coordinate workshop. And to have all these work properly, we got to set up what's called a virtual environment. There are the commands listed down here on the GitHub repository, right about the middle, but you're gonna basically want to, yeah, correct. So there's one additional command. You're gonna go Python 3-m module venv virtual environment, and then you're going to create the folder the virtual environment will exist in. So it's Python 3-m venv. With the note, if you're on Windows, it's not gonna work. So I don't know how else to say it. I've worked with Mike on this, but yeah, maybe you can help if anybody's on Windows, how to get that set up. Is anybody on Windows?
Oh, yeah.
Thank you, appreciate it, great job, awesome. Okay, so you create the virtual environment. This usually takes about a second because it's copying all the binaries, et cetera, over. And then now you have to activate it. This is where the commands are actually complete here. So source, virtual environment, binary activate. You notice this shows up saying you're working in this virtual environment here. And the next portion is you're gonna have to install the requirements themselves. So I created a nice little requirements.txt file. Boom. Okay, so I actually need a wallet myself. Oh, I'll find one. I can find one. So, okay. So next, as part of going through this demo, we're gonna use the wallet balance checker script. So we're gonna make sure that everybody in this room has a coordinate balance according to the coordinate node, which I've already loaded with between about 1 and 2 coordinate testnet Bitcoins. Remember, none of this is real. It's all in testnet 3. It's gonna get blown away anyways, so don't get attached. So, wallet balance checker. And there should be a balance.py file in there. And then, because you've activated the virtual environment, Python balance.py. It'll ask you for a wallet name. I'm gonna do, I know this one has a balance, acid. And you should get something saying that you've connected to the node and we're able to see 1.97. I should have wrote TBTC on that. Is everybody able to achieve that? You got one? Okay, nice. I think there's one with 3 in there somewhere. So, okay, perfect. And by the way, for the sake of this demo, please do not just there are definitely functions where you can just drain all the wallets. Do this after this whole exercise. This is just a shared community thing, how you can interact with this. So I want to show one thing as well. And by the way, how much time do I got still? Oh, I thought Charlie knew. Okay, I'm gonna keep going until the. Okay, that's great, perfect. Okay, so as a side note, I just want to show this that. Oh, sorry. Most of this stuff, in terms of interacting with a coordinate node, so you literally just download it in the same way you do Bitcoin, but it uses the exact same JSON RPC methods as Bitcoin Core. So get balance, all that is literally the exact same. So next is, did everybody have a balance? Or was able to find a balance? Okay, cool. Next, let's go create an asset, and then we'll sweep the wallets to conclude. So in the, I believe there's another directory, there is a wallet asset tools script.
I already asked 8 minutes.
8?
We
Can I have an extra 5? Okay, I think we can do this. So, okay, next. So to best see this, I just want to show here, but in this example, if you can actually navigate the directories, there should be a couple of different assets. We had one for tabconf. We had just the generic one we did initially, and then there's an op next. For the sake of this demo, if you want to in your local directory, you can actually just replace this asset with any PNG you would like, but it must be below 1 megabyte in size, because that's the size of the blocks. And then a side note is you will probably have some relay issues as well for that. So yeah, just try to do something small if you want to keep it or change that. As of right now, it's still, sorry for holdover from tabconf, but that will be your default asset is in the asset.png file. But you also have in this the wallet asset loader. So what this does is, this essentially is a script that will run through and it will grab that asset file, it will serialize it, and then obtain the hash necessary to go into the coordinate blockchain in your transaction so that it basically, you can prune out these assets in coordinate because you have the original hash along with it. So if somebody does have the data, it can be available, but if not, the hash is still stored in the transaction itself. So going down even further, there should be a section commented out. Uh-oh. Did I miss this? I think I may have made a slight mistake. I don't think so, though. Oh, here's the location. Okay. So if you go into the wallet asset loader.py file, on line 176, there is a section you can edit for your asset that you are going to create and send to your wallet. So from here, I want to give the asset a title. By the way, was everybody able to find the wallet asset loader? Okay, perfect. Yeah, so on line 176, you can go below and you can modify this. I'm going to do op next NFT. Let's do that.
Do we need to modify this?
You don't have to modify it. You can absolutely send it if you would like. I just want to make it so you can see like there is the ability to customize and create kind of like what you want. So headline op next is awesome. There we go. Okay. So I'm going to write that file. Okay, now the next thing we're going to do is we're actually going to run this, but you're going to need a coordinate address to send this asset to. So we are going to essentially go to the Enduro wallet, log into wallet, and if you did everything right and didn't do the security settings for testnet, you should be able to just click the CBTC, get a receive address, copy that in, and we're going to use it here in just a moment. So Python set loader.py. It'll go through all the wallets and select the wallet number that belongs to you. It should have balances attached to these as well. By the way, does anybody have the wallet affair?
That was actually him. What? Ed. Oh, affair.
Ed, okay, I'm taking affair. I'm going to use it. So you should be able to enter in the number of the wallet that matches yours. And so basically it shows now, like you have a change output value, so that's showing you the change you're going to have. This is the hash of the asset that you're creating. And from here, you need to paste in the address you want to send the asset to. So in this case, TC, testnet coordinate 1. So then you'll get unsigned transaction created successfully. The next portion is the wallet on the coordinate node must sign it. Press enter to sign the transaction. If you want to look at the Python code, you can see underneath the hood. And then the last portion, I was doing this for debugging, but you can press 1 to broadcast the transaction, which you will want to do. Anything else just to skip it. But let's broadcast the transaction. And you should get a TXID at the bottom saying it's been broadcasted to the coordinate sidechain network. And that will show up as, what? It showed up?
Nice.
Yeah, op next is awesome. I should have done not the tabconf logo, but essentially this basically means you have an asset issued on the coordinate network. This is not on testnet. This is on the sidechain itself. The data is stored on the sidechain. Whether or not it has any value or any use or anything,
Yeah, there's
Probably
there's
not.
no indexer for it. This is native
Yeah,
consensus
this
to
is-
the chain.
yeah, so with that said, yeah, that's kind of the cool part about it. And then from here, you could transfer it to other
And
people.
it itself is a UTXO. So yeah,
Yep.
you know, you can divide these as you could Bitcoin.
And so over the next couple of minutes, it will probably confirm. And because we're using the mining side, so we have RBF.
Yes, we do have
Or
RBF.
CPFP. So that means
CFP.
I bet I can sweep the wallet for the rest of the money. And I have a sweeping script as well that we're going to move on to. So we're going to go back to those wallet tools. So wallet tools. And then we're going to run Python sweeper.py. I did reuse this function, but I'm going to take a fair again. $49. See if it'll let me sweep. Oh, I need to send it an address as well. So let's grab my Enduro wallet address. I just would rather just make sure.
Yeah, it didn't
Yeah,
like
it didn't
'cause
work.
it's
I'm
pending.
assuming because it's got it in flight right now.
Yeah.
So you're able to sweep as well? Oh,
Nice.
congratulations. So awesome.
Well, it'll settle eventually once it gets mined, but yeah.
Let me try again. But yeah, so that I think concludes my demo of basically like how to use Coordinate, interact with the wallet, create an asset, and sweep the funds away from a public node. Please, in your own case, if you do decide to work with Coordinate, download the node and run it securely. And yeah, don't share a node with 50 wallets. Each one of these, by the way, is full of CBTC from testnet. So if you want to go through and sweep these and then do the peg out process or the wallet convert, you can actually just convert all this right back to testnet Bitcoin into your wallet. So you have one more shot.
Yeah, the other thing, if you get a shot to play around with it, is the pre-confirmed transactions. It's pretty cool. The premium transactions in the wallet. It uses a reserve fee market bid system to where it loads it full of fee-paying transactions, but you just set a reserve amount, and you never pay more than it takes to buy the block space. So if it doesn't meet your reserve amount, the transaction is just canceled. If it does meet your reserve amount, you never overpay. You only pay minimum it takes to get in the block. So no RBF games.
I want to point out one more thing as well. In the GitHub repository, there is, you can view your transaction on the Blockchain Explorer Cortiscan. So it's basically just a very basic blockchain explorer. It's not like mempool.space level, but if you did get like a TXID from that exercise and you're wondering like what's going on, where is it? You can paste it in there. It also has the times of the blocks, and it looks like we haven't gotten any mined blocks yet. So
Any questions?
So you said when you sign the transaction, sending it out to be signed, how does that work?
So basically what's happening is that you're generating a transaction using Python from a local node. And when it brings it back to you, right? So it sends it back to your client. And then your client just sends that back to the Bitcoin node through a fund raw transaction to basically sign it and fund it for the value necessary. And so basically you're interacting with a remote node is what I'm saying. You're not actually doing any of this locally. Like that Python script is not its own coordinate node. This is completely, you're trusting somebody else's infrastructure. That's what I meant by that. It's like, yeah, we're done. It went great.
Rock on. Cool.
Yeah. Thank you guys, appreciate it. Yeah, and feel free to take all the CBTC or testnet from any of those wallets. I don't have any conferences coming up for a bit, so.
good to go. Hold on. So, hey everybody, my name is Trey. I work at Alpin Labs on Strata, which is our, hopefully soon, a roll-up project. It's not technically meeting the definition of a roll-up yet, but that's what we're working on. So I'm here with Sims. Do you want to introduce yourself?
Hey guys, I'm Sims. I'm also working at Alpin Labs with Trey and a bunch of people working on this bridge, so I'll also be presenting on some of this.
Cool. So today we're presenting like the bridge part, which is the hard part of making a secure bridge between Bitcoin and the roll-up settlement domain, which is kind of hard to do because of a couple of reasons. So what are the limitations Bitcoin has that like pose an issue for us? The first one is script is obviously pretty inexpressive. There's a lot of reasons for this, historical, but it's the most sophisticated math you can do is just addition of 32-bit integers. And you can't even really easily handle overflow. You kind of have to do some hacks. And so that poses a problem for doing logic. You can't sign data directly. You can sign a transaction, but you can't actually control the message from the script. The message is always about the transaction. So being able to use the normal signature verification Bitcoin supports isn't an option. And you can't control spends from within the script. So covenants, we don't support those. I think it's pretty much impossible as it is today, barring maybe the pipes thing in an hour, to like control how a transaction gets spent at all from within script. Caveats to that, obviously. But we do have solutions to these problems. It's double. Yeah, data dependently. You can't control the spends data dependently. So the solution to script being inexpressive is act like hardware, shuffle the bits around, do a bunch of stack manipulation. If you want to have some sophisticated logic, you can use a lookup table. It's a whole bunch of branching ifs. It works, but it's gigantic in script, so we have to like find ways to deal with that. Signing data, we can fake it with Lamport signatures, or what BitVM does now is Winternit's one-time signatures, which are a little bit more compact, but more complicated to pull apart. And so you can control the spends by doing it optimistically. So you have a different UTXO that gets spent in a certain way, and then if it gets spent in the wrong way, you punish it. And how we do that is part of the hard part. So explain like I'm 5, how does a BitVM-ish bridge work? So when user wants to deposit funds into the rollup, there's some process to lock that up, and the funds get put into a deposit UTXO. And at that point, that is no longer like their UTXO. It's decoupled from the user, and the user's funds that they're controlling are sort of transported into the other settlement domain. And so that deposit is now part of the bridge. It's not like tied to the user in any way. So it's like sort of an indirect way to do it, because when we think in Lightning, those UTXOs are still yours, they're just half yours. But in a BitVM bridge, once the funds are deposited, it's like the ownership has been teleported into the rollup. And so when it comes time for someone to withdraw those funds, we have what we call an operator front the withdrawal. So they have some funds of their own, and when they get the message to say that we want to do a withdrawal, they make the normal transaction, and the user gets those funds. Could be the same user, could be somebody else. And then for the operator to get reimbursed, we have some process to spend the deposit as the reimbursement back to the operator if they've done it correctly. And so there's a little bit of magic there, which we're going to explain in this slide. So the process of doing the deposit, so this is going to be actually going into the details a little bit more. The full explanation wouldn't fit on the slide, but this is still like the intuition for how it should actually work. The user fronts, or the user doesn't front. The user creates the deposit request. And so this includes in an op return like the address they want the funds to end up in the rollup. And the group of operators, which protect the funds, start pre-signing a bunch of transactions off-chain. And so this is faking the covenant system by using just a big, fairly large is the goal, mu-sig, n of n multi-sig. And so that's where we get our 1 of n honesty assumption. So they set up a whole bunch of pre-signed transactions, which I'll show in a couple seconds. And then once that's set up, they accept the deposit request by sweeping it into the actual deposit UTXO. And if that doesn't happen within a couple hours or a couple days, it depends on how we want to tune security parameters. These could claw back that UTXO right after the deposit request transaction back to themselves. It's not shown. We assume it works in that happy case. So that can stay there sort of indefinitely. There's no like time locks on how long the deposit UTXO needs to be there. There's no like refreshing system. There could be a need for that in the future for fancy features, but in the simple version, there's no need for that. So when it comes time to do a withdrawal, in the cooperative case, assuming everybody stays online, all the operators stay online, they could just spend it directly and process the withdrawal immediately. So that's the cooperative withdrawal transaction, and the user gets their funds back immediately. And so that's assuming that all of the operators stay online indefinitely. This could happen because they're incentivized to stay online, but we can't rely on that. So we need to handle cases where somebody goes offline. And so we call this the uncooperative honest path. So after some period of time, maybe it's an hour, maybe it's a day of the cooperative withdrawal not being handled immediately, we fall back to the uncooperative path. So somehow we pick an operator. That's part of the consensus logic of the rollup. We pick an operator and tell them, here, process this withdrawal in this way. And so they do the fronting. They send the transaction. The withdrawer gets their money. And then they try to claim the deposit. And so the way this works is this is where the BitVM stuff happens. The stuff in the box is the actual BitVM game. So part of the pre-signing, all of these darker blue boxes are pre-signed transactions. Part of the pre-signing is to create an instance of the BitVM game for every possible operator that could be assigned to process that withdrawal. So this end of the path there actually has, if there's 100 operator, we assign 100 different instances of the game. So they create a zero knowledge proof saying, I process this withdrawal correctly. So they reference the transaction and they reference the previous state checkpointed for the rollup on Bitcoin. And the statement of the zero knowledge proof is, I process this withdrawal according to how it was assigned in the last checkpointed state. And there's a bunch of stuff to reflect, like look up where the transaction is in Bitcoin. It's a pretty big proof, but it's just a regular Groth16 proof. And we actually can verify that in BitVM reasonably well. We'll explain that in a little bit. So they attest, or assert is what they call it in the terminology. They assert a certain version of the proof. We don't have to verify it immediately. We just have to assert that we've constructed it. And so that begins a countdown. So there's a time lock on one of the branches of that spend. And if everything goes well, after a challenge period, which could be between a day and a week, we only have to do one round of this, then it allows this reimbursement claim transaction to be spent. And so they get to spend with a connector output to get the funds back. And so that all works out. But if they lie and they submit an incorrect proof, so they didn't actually do the withdrawal transaction as they were told to, maybe they made it differently, or maybe they just didn't make it at all. Somehow if they haven't done it correctly, then they can't construct a valid proof. And so someone could find a problem with the proof. And so one of the spend paths they can pick out, and anybody could be a challenger. They look at all the different constraints and see which ones got violated and submit a disprove transaction. And so this spends one of the tap branches, and the script on this transaction checks, did the actual thing get violated? And if it did get violated, then they can spend the connector output to themselves, and then the operator doesn't get the deposit, and the deposit's safe, and Strata can identify that this happened, and then assign a different operator, and we can retry the whole game again with a different operator. And so we can keep going through this until we find an operator that's honest or bail out. So this is the simple version. This is the intuition. There's a bunch of connector outputs that haven't been drawn because it would just be too much to fit on the slide and explain right now, but we'll show it in a bit. So I'm gonna move on and let Sims pick up from here about the snark verification.
Thanks, Trey. Yeah, so what I want to get to is like the core intuition for how this works, and at the heart of BitVM2, BitVM, and all of the bridge designs based on that is this idea of being able to verify a snark on Bitcoin, having Bitcoin be having the ability for someone to make a claim about a snark, which is a claim about arbitrary computation. So snark proof is about 250 bytes, and it's a cryptographic proof attesting to arbitrary amount of computation being correct. So if someone can make a claim about a snark on Bitcoin, and we have this one-round optimistic process, meaning anyone can challenge that claim, and Bitcoin's able to resolve who the winner is, then we can really construct some very interesting things like cryptographically secure bridges that allow Bitcoin to go in and out. The problem is snark verifier, snarks are small, can be small, 250 bytes, but Bitcoin scripting is very, very limited, and the verifier computation just to verify a snark is, and this is after like 6 months of research and further optimizations, we've gotten it down to 1 gigabytes. It's obviously way too big. That's not going to fit in any Bitcoin block. And so, how does that work? Like we script is not very expressive, and so 1 gigabytes just to verify snark. That's the main problem, and this is kind of where the core insight of BitVM2, led by Robin Linus, came from, which is, what if we split this, giant 1 gigabyte verifier script into a bunch of different subscripts? Like we just split up that program into a bunch of different smaller programs, and instead of having to, spend the verifier, which is 1 gigabyte, that's not possible on Bitcoin, we could spend just one subscript, because the core sort of intuition there is if the snark is valid, then every subscript has to be valid. And if it's invalid, then at least one subscript is going to be invalid, and you could just spend that one on Bitcoin. Right, so that's the kind of core idea of BitVM2 and how you can get to an optimistic verification of a snark. And what's important and quite interesting is that this can be done just with one round, meaning, like when someone makes a claim about a snark, someone challenges the snark, it doesn't have to be, back and forth, many rounds of the challenger and the claimant going back and forth until Bitcoin's able to resolve who the winner is. In protocols like on Ethereum, like the optimistic bridges with Optimism, that goes through 73 rounds of back and forth before it's determined. In Bitcoin, we can do this with one round, which is very exciting. Interactivity is low. And the reason that we can even do this kind of like splitting up the snark into a bunch of subscripts and only having to spend the one subscript that's invalid is because of Taproot. Taproot allows this really nice abstraction on the computation where you have a tap tree. Each of the subscripts can be a tap leaf, and what is actually on chain is just this Merkle root, at least when you initiate that claim. So visualizing, for folks that are more visual than words here. This is like, a high level sketch of what's going on really. Like there's the input to the snark, which is gonna be, on the order of a couple hundred bytes. And there needs to be, some computation run to determine whether it's valid or invalid. This is in Bitcoin script, by the way, that's 1 gigabytes. And instead of doing that as one big script, we're gonna put these in a bunch of subscripts where the input goes to this subscript, which runs some steps of the computation, has a output state that is passed into the input of subscript 2, which runs some computation locally, gets an output state, state 2, and that is passed into the input of state 3 and so on. And so this is really interesting because each subscript is much, much smaller. And what in this case, what the operator, so when we build the bridge design from this kind of primitive, the operator, if they're challenged, they only need to commit to the bit commit to all the states in between these subscripts. And it turns out it doesn't even need to be a big state. It could be 16 bytes. It could be a 16-byte hash that take the input, do a bunch of computation, whatever might be a bigger state, might be a bunch of field elements, turn that into a 16-byte hash. That is the state that you're going to pass into the subscript 2, which then in the input you can pass whatever the actual state is instead of the hash, and subscript 2's going to verify that that matches and then use those inputs. So you can do these kind of clever tricks and really get the commitment down quite a bit. So that's the core intuition behind this idea, but building the bridge itself is another whole thing. And what this at least allows for is for Bitcoin to reason about the valid state of a side system, something outside of Bitcoin, like a rollup. It allows Bitcoin to reason about that. That means you can do withdrawals, cryptographically securely on that. So, from that idea, there's kind of a recent paper done by Robin Linus and collaborators on the BitVM2 bridge design overall, like taking that primitive and turning that into a bridge design. At Alpin, we've been kind of, for the Strata bridge, we've been making a bunch of improvements to that design. So I just wanted to highlight a couple of those improvements to the design. We'll be releasing the full Strata bridge design quite soon and sharing some of that here as well. But essentially, one of the core concerns of the BitVM2 bridge design as it's available on the preprint is that the liquidity requirement is really high for that bridge. It turns out, at every time there's a deposit on the BitVM bridge, you might have 10 operators, and each of these 10 operators need to lock in some stake. And so, if you have like a deposit value fixed for 50 Bitcoin, the staking might be something like 2 Bitcoin, but you have 10 operators. Each operator needs to stake to lock up 2 Bitcoins for each of that deposit. And so suddenly the liquidity requirement for doing that kind of bridge looks to be pretty high. I mean, it could be even as high as maintaining 50% of all the deposits in a collateral, which doesn't, we want it to scale to hundreds of thousands of Bitcoin that's locked up. That's going to be very expensive. And so we have in our designs a way to actually reduce that to having one O of one or some constant number of stake per operator, but doesn't scale with the deposits, which is nice. Collateral reuse frequency matters a lot as well. If an operator is fronting some capital to the user, when can they expect to get that back from the bridge? If it's a long period of time, then that slows down what the withdrawal capacity of the entire bridge is. And so in this process of fronting and reimbursement, being able to reduce that collateral reuse frequency down to a few days is actually quite important. This is something that explicitly our bridge design does. I think in the previous work, it's 2 weeks, or I think about 2 weeks or a little over 2 weeks is the fastest way to reuse the collateral. We also incorporate standard transactions for an operator defending a challenge. Before it was non-standard transactions. This is important because if challenged, the operator shouldn't have to go rely on some minor, and that's another trust assumption for the operator to be able to include. And so what I mean by standard here is within the standardness limits of each transaction being at most 400 kilobytes in size, V-bytes in size, and in the earlier design it was up to 4 megabytes, so which would have been a non-standard transaction. And then overall, due to some of these improvements, increasing the withdrawal capacity, also through concurrent reimbursements processed by multiple operators. This is very important because we don't want the withdrawal capacity to be very limited to, having one operator means that operator might, front some users' money and then is waiting for that liquidity to come back, but maybe a bunch of other users are requesting withdrawals. So we looked at some numbers on WBTC and these kinds of existing bridges and sort of mapped out that we need to have at least a withdrawal capacity of, being able to withdraw, again, at least 100,000 Bitcoins every year. And I think we can meet that without going, within practical limitations here. This is explain like I'm maybe, much older version of this. But this is a idea of some of the layout. I don't think I really need to go too much into this, but essentially what the kind of layout shows is that there's a deposit. This is of the bridge itself. The peg-in up here is a deposit that had happened to the bridge. The bridge out over here is some kind of payout that is made by the operator to a user that's requesting a withdrawal. And then immediately the operator kicks off a reimbursement request from the bridge. So I think we can shift over to the video, which is going to be a little bit confusing because it's just the terminal running a bunch of things, but I'll try my best to narrate over that. So maybe I'll give you a YouTube link.
Oh yeah, sure, let's do it that way. Did you DM it? Yeah.
Do volume off.
All right, so here we go. I'll let Sims explain.
So, let me pause can you pause? Okay, great. It's water. So, maybe some context on the sequencer you can provide.
Yeah.
Share that, and then, yeah.
So for background on a rollup, ours takes the form of a blockchain, and periodically we checkpoint this blockchain by making a zero-knowledge proof for a batch of blocks, and that batch is somewhere on the order of half an hour to 2 hours. We're still trying to figure out what makes sense, and those blocks come out somewhere on the order of 1 to 15 seconds. We're still, again, trying to figure out the numbers, but just for an idea of the scale of things. So these blocks currently are being produced by a single sequencer, which could be decentralized in the future, but our goal is to get the bridge working first. So single sequencer makes things a lot easier. So the sequencer produces these blocks, and then they periodically prove all the blocks, and then prove a batch of transactions, and then make a bunch more proofs for reading the deposits that are getting made from layer 1, and periodically submit the checkpoint to Bitcoin in an inscription along with all the data. And so once the checkpoint has been made, then we can start acting on any deposit assignments that have been made as of that checkpoint. And so that's what lets the operators make their own withdrawal proofs to actually claim their funds. So in this scenario, we have the sequencer running in the upper left, and on the right, I believe, is an operator that's about to get an assignment. And I have a question over there.
Yeah, I was trying to understand. So you're checkpointing and then you're submitting, or you're going to push that in an inscription on chain. Like, what is the data that's in the checkpoint? Is it like everything, or are you going to have to? Like, it's not going to be all the transaction data, right?
Yeah, so it's there's the proof itself, some data about like the previous block height, the current block height, the block height on Bitcoin that we've read up to, and state commitments for all of that. We're also including, the plan is to include the state diffs or change sets to all of the state entries that have been made. So that's kind of big, but that's what makes a rollup secure. That's important for the security proof. Because you have to be able to reconstruct the state to be able to do forced withdrawals and stuff, which we're not going to talk about today. But yeah, it is actually like most things. It can be kind of large, which we'll just expose as fees.
So then, is there like a separate process to, like, you know, if you want to if there's any kind of challenge or something like that, you have to request the data that then you like recompute and say like, okay, look, yeah, commits match up. It looks like everything's okay on like.
So that's actually part of how rollups are secure is the proofs can't be constructed unless that data has been posted on a Bitcoin. So we include in the proofs like the checkpoint proof can't be constructed unless you have a proof that you've inscribed the preceding data up to that included. There's a bunch of steps to it. Maybe we should have made a diagram of all the different proofs.
I don't know if this works, but yeah, and to be clear, like a valid checkpoint proof can't be made, right? Like so, there's like these inscriptions on Bitcoin made by the sequencer like provide checkpoints, you know, at those points of what is the, you know, latest state of the rollup. Like someone is able to take that checkpoint, look at the data, see the proof there, see the claim about, you know, what the new state root is, and verify the proof, and you know, immediately get to what is the latest state of the rollup. That proof itself is part of the withdrawal statement when bridging out. So when an operator, you know, fronts the user, now it's trying to withdraw from the BitVM or the Strata bridge, like the BitVM2-based kind of mechanism there. They would construct a proof that, you know, verifies, you know, it shows the inclusion of a checkpoint proof made, you know, by the sequencer on Bitcoin to just show this is the latest state of the rollup. That proof is actually verified as part of the proof statement, you know, so it's like a recursive verification of that proof as part of the withdrawal proof. Yeah.
I have it's like very simple question. As I was like, what do you really know that is really needed? What is this?
I don't know what they meant by that.
Oh yeah, so in this demo, what we were showing is basically we're going through the flow of there's a pre-signing, there's a deposit that happens. We basically, and then, you know, some activity, maybe that like deposit makes it on the roll up, like, you know, people can spend and do things there. Then there's a withdrawal request, and the operator fronts the user for the withdrawal and makes a valid claim actually. So like, let's say they actually front the user and makes a valid claim. Someone challenges that operator, even though they've made a valid like snark. In that path, you know, the operator has to do some assertions on like what those intermediate states were, state hashes, and a disprove doesn't happen because the operator is honest, and like no one can disprove that. Like they can't spend any of those subscripts, if that makes sense, like of the snark. So no disprove is needed for an honest operator. But if they're challenged, they have to assert, and you know, because they can't be disproven, they will just be able to get that reimbursement back after some time.
Last question.
So this is the happy path, basically. I don't think we got the video together for the unhappy path, but
so this is the unhappy path, but like of an honest operator.
yeah. So the uncooperative happy path.
Yeah.
Yeah. So I don't know what you guys want to see from this, but oh no, you do.
I guess this is like my token question. Where does the name Alpin come from?
Where does the name Alpin?
Yeah.
That's a great question. I don't think we have an answer to that. Scaling mountains, Alps. the cereal or muesli, if anyone's familiar with British muesli, it's the #1 cereal in UK. Cool.
Cool.
If there are any other questions, find us or do we have
One
time?
more at the end.
Yeah, Scott. Yeah, just, it's okay. It's small.
People on the stream.
Yeah, a little bit away from the demo. This is super cool. Thank you guys.
Nice.
Just, yeah, kind of more broadly, like what are you guys most excited about in terms of use cases to support when you do get to production?
Yeah, I can speak on that. So, I mean, first, access to BTC off-chain in cryptographically secure ways is a big deal. This is one of n trust assumption. We don't have covenants yet. If we had covenants, it could be even better. We don't even need counterparties, right? Like for that pre-signing, but just the access to BTC and even in this one of n is a big deal relative to where things are today, which is like 2 of 3 or 11 of 15 or something like that. And so use like basically financial services around BTC that we can use, right, without having to rely on centralized entities to provide those services. That's what's exciting. So the ability to borrow against my Bitcoin, do payments faster, better UX, open up innovation for BTC by making it fully programmable. I think that's what's exciting. And then, of course, privacy.
Roll-up supercharged Lightning, in my opinion. There's a bunch of really cool things you could do with it, and you can route payments through a channel that's in a roll-up without having to have funds in that roll-up. It's a bunch of cool ideas you can have there. We're not going to go into those today, but anyways, back to the presentation.
We got about 3. Can we speed through it in like 3 minutes?
What's that?
Can we run through it in like 3 minutes?
Oh yeah.
Yeah. Cool. Okay, so demo. So the opcodes that would improve this, we can improve it by a lot. There's no reason not to. So CTV would basically make all the annoying interactive pre-signing stuff just be non-interactive. There's like a couple of caveats to that, but it makes our lives a lot easier to have covenants, like proper covenants, even if they're not super sophisticated. CTV alone would go a long ways. TX hash would make it a lot better. You could simplify certain things. We're not going to go into that, but CAT obviously would make our lives a lot easier. If you had CTV and CAT together, you wouldn't need TX hash, and a bunch of things could be simplified. You could directly verify Merkle proofs. You could verify Stark proofs reasonably easily. The nice goal we would like to achieve is be able to just directly verify the snark in Bitcoin script without having to do the challenge game. That's a bit harder, but we believe it's possible. And that would let us get rid of the challenge game, and so you could immediately handle the withdrawal directly. GSR, again, would be great, would be fantastic to do that. Any improvements to make it more powerful would help us a lot, and just reducing the script size. And bonus 2 would be check safe from stack, so that we wouldn't have to do the big giant Lamport signing games. Alone, not super useful, but with CAT and would that help us a lot. Cool. So, and then I have a different form of this slide. It's a little prettier if anyone wants to take a picture. Okay, so that's about it. If you want to learn more, go to stratabtc.org. There's a link to the GitHub repository that has the bridge demo, so you could run through it yourself. It's still sort of a work in progress, but it does work pretty much.
And we're about to open source a lot of the code that's gone into this very soon. So follow along. You could run the bridge yourself. So along with a blog post coming out explaining everything in more detail. So
Thanks, guys. Yeah, thanks a ton. Thanks a ton. Bring Alex up here, get you set up. as I said, yeah, we're 10, 15 minutes late, but that means, but lunch is right after Alex. There's a cafeteria out here to the right, and at like 12:10, that'll open up. Otherwise, we are bumping the pipes workshop. That would be right after this. We're bumping that to immediately after lunch. And also the corresponding talks over on the presentation stage, one after lunch. But Ethan over there with Kat is about to start. Either he's already started or he's about to. Otherwise, Alex.
Yo.
Go for it.
Okay. What's up, everyone? I'm Alex B. I'm at Arc Labs. We're working on one of the two current implementations of.
It's whichever you prefer.
Yeah. That's this. Okay. That's gonna be easier. So yeah, we're working on one of the two current implementations of Arc. The other being the second team. And today I'm going to be talking about some of our vision around Arc and why we think it's a lot more interesting than perhaps people give it credit for. And so let's just dive into it. I will say this is not going to be exactly an Arc explainer. So hopefully through some of the stuff that I present, you guys will be able to pick up some sort of intuition for how the system works. I'll be giving some details. If you have questions, please feel free to interrupt. I don't have a lot of slides, so we should have time for questions. So yeah, let's go into it. And so first I want to talk about the genesis of Arc. So this is not my table. This is a table that was put on the very first release blog post of Arc originally last year. And so the reason I bring this up, and perhaps you'll find it a little bit confused, at least I did when I originally saw it. But the reason I bring it up is that there was a very intentional focus when Arc came out as to what exactly the purpose for Arc was, which is that it was to scale payments. It was originally designed basically to perhaps even compete with Lightning, or at least provide an alternative to Lightning. And the focus very much was on like mobile flow, retail payments. And there's a lot of decisions that were made because of that that actually highlights this focus. So, I mean, what is Arc? Very briefly, we have a shared UTXO protocol, right? And it's a round-based protocol. So we have periodic creation of on-chain UTXOs, which are nesting or splitting a bunch of what we call virtual UTXOs assigned to various users that are joining this round. And one of the decisions that was made to be able to create great UX around payments with Arc, at least in the original proposal, was to have 5 seconds rounds. And so as you can imagine, 5-second rounds, it means 5 second a new on-chain UTXO is created. And so obviously, I mean, one of the criticism or feedback, or at least sort of like reaction to people was, well, this makes a whole lot of transaction, and perhaps there's a sort of like a limit to the amount of like Arc that we can have running on a network, because they're going to be filling up blocks pretty quickly all by themselves. Another decision that was made was around the expiry of the Arc VTXOs, right? And so in Arc, the on-chain UTXO that is created has an expiry because it needs to eventually return to the Arc server, which is the liquidity provider that provides the liquidity for those on-chain UTXOs to be created. Now, because that expiry exists, the motivation there is that the users need to be able to roll over their funds that are in Arc into a new shared UTXO if they want to preserve sort of like sovereign and unilateral control over it. If the UTXO expires, then eventually it essentially becomes custodied by the Arc server. And we don't want to have that, right? Because we want to have Arc be sort of like this self-sovereign layer 2, whatever you want to call it, but at least you want to have it so that only you can spend your funds that are into an Arc. And the decision as far as the expiry that was taken was, well, let's make it 4 weeks, right? Because the idea is where you're serving mobile users, and so you want to have it so that you allow them enough time to be able to come back online to roll their UTXO over, because this is not something that happens automatically. Someone needs to intentionally make a transaction for them to roll their UTXO over. And so the idea is, well, obviously, if you have funds into an Arc, you don't want to have it so that, like, you go offline for a couple of days, camping trip or whatever, or your phone breaks and you need some time to get a new one, whatever it might be. And by the time that you're offline, your VTXO expires. And so the decision was like, okay, let's make it 4 weeks. So that seems to be enough time for someone to come back online, refresh, and kind of like reset the timer, right? And that 4-week period has a sort of like very serious effect on the liquidity requirements for the Arc server, because the Arc server needs to commit funds to on-chain UTXO, and they will not get those funds back until that 4-week expiry period. Now, there's some techniques that we've shared just recently that might allow the server to kind of like work around some of these issues, but anyways, the idea was, again, we're targeting mobile payment retail users, so we want to make it easy for them to come back online and so like rotate their UTXOs. And obviously another, I think, major component, and probably like one of the things that was, put emphasis on when Arc was released was, well, you need covenants, right? You want to reduce the interactivity, and so you want to make it so that you don't want the receiver to have to be online to receive. So you want to be able to have the receiver be offline to receive payments, so that we work, the idea was to do something better than Lightning. And currently with Lightning, unless, there's some workarounds around this, but effectively with Lightning, someone needs to be online to receive the transaction. So all of that to say is like those sort of like parameters that were created around Arc were very specific to the payment use case. And following the release of Arc, Ruben Thompson actually, as wise as ever, came up with this scheme, was like, well, actually, maybe we don't need covenants to be able to reduce the interactivity and make it so that, we don't need the user to be online to receive payments. How about we just make it so that the receiver is actually the one that will be joining an Arc round and settling their virtual UTXO by co-signing this shared on-chain UTXO. And in the intermediate state, what happens is if I want to send someone an Arc payment, I'll just co-sign with the server, and me and the server are going to agree that we're going to add a spending condition to the existing on-chain UTXO, or at least my share of the on-chain UTXO, and we're going to say like, say if I send some Bitcoin to whoever, Charlie here, some VTXO, we're going to say like, okay, now Charlie and the server can collaborate to spend this virtual UTXO and create a new, and therefore swap it against a new one in a new Arc round. And obviously, even with covenants, what we realized was this is probably the preferred way to go. And so what we've been doing at Arc Labs right now, while sort of like implementing the protocol and figuring out all of the details that I think, people haven't really, because the fact that it required covenants and the fact that there was some kind of like pretty curious liquidity requirements sort of like led a lot of people to kind of like dismiss Arc, or at least put it to the side, because they figured, well, unless we get CTV and some other stuff, it seems that it's not quite workable. Today, we're focusing on an implementation that does not require covenant. It effectively just uses pre-signed transaction. And obviously, we're working quite a lot with the method that Ruben involved, because we think this is what leads to at least the best payment experience on Arc. But what does that look like? Well, I mean, we've been working on like this proof of concept wallet, and it's not something that we're going to release in production. This is not something that we expect will be available pretty soon, because there's quite significant UX challenges with Arc that I think just seeing this right now will give you an intuition for what those involve. So obviously, you want to receive the flow is the exact same one as any other Bitcoin wallet. You just get the address, and then you paste that from the sender side, and we'll just send 5,000 sats. And we're going to make the payment. Now, obviously, the payment happens very quickly from the sender as well as from the receiver side, because what we're doing is we're just co-signing with the server, and we're saying now this guy can spend it. So that's pretty much instant. But this is not an actual settlement, because from that point, this is what we call an out-of-round transaction. Remember that adding a spending condition to the existing virtual UTXO does not remove the existing spending condition, which is I still have the opportunity to co-sign that virtual UTXO, even if I added the spending condition, sending it to Charlie. And therefore, if the server decides to collude with me to double spend that transaction, we can still make that happen. So it's not fully trustless in the way that we are expecting of Arc. So what does that mean from a UX perspective? Well, what happens is we have a pending transaction. And so that pending transaction, that balance is available to be spent, but it has a what people have been calling a state chain trust model, right? Where you're trusting the people that the person that sent you the transaction and the server not to collude to double spend it against you. And so obviously what we want to have happen is to have the same security guarantees as Lightning, right? So what needs to happen is the receiver needs to actually settle that transaction, put it into a round, and create a new virtual UTXO where the spending conditions are only Charlie and the server. And so what we do is, we just go ahead and settle that transaction. And what you'll notice when we settle the transaction is this takes a little more time. This is a little more involved than when the sender sends the transaction, right? Because what's happening behind the scene here is that we're requesting to join a round to, so actually what happens is the server says, hey, we have a round coming up. I'm going to put an on-chain UTXO. Who wants to join this round? So what happens is, the client registers this virtual UTXO. Charlie says, hey, I have this virtual UTXO that Alex co-signed for me. Can we join a round so we can create a new one for me? And therefore, there's some interactivity there, right? And obviously that interactivity potentially scales with the number of people that are joining that round. There's a lot of message passing happening, and so it's not as instant, and it creates some kind of friction around the UX. And this friction is going to remain there, and is probably, even if we have Covenant, always going to be some trade-off as to how people decide to build payment use cases around Arc, because at the end of the day, maybe people decide to do just out-of-round transaction. It's kind of like a new trust model, right? It's probably better than custodial, but you're still kind of having to trust some entities there. But our focus at Arc Labs is not necessarily on actually building payment use cases for Arc, because we recognize that there's a lot of challenges, and we're looking forward to work with people to kind of solve those UX challenges. But we think that payment is actually perhaps the tip of the iceberg for Arc. And so the way we're approaching this is that, actually, what are virtual UTXOs, right? They're just like UTXOs. We think that Arc can be used as this generalized construct, not only to do virtual UTXOs, but to do virtual anything as long as you have UTXO-style scripting on Bitcoin. So Arc potentially scales any type of Bitcoin script because, if we actually look and this is an Arc Explorer. This is the first time we're presenting that, and it's just kind of like a little tool that we created because like what is actually happening? What are those virtual UTXOs, right? They're just a taproot tree, right? And so maybe we select from this one, which is, okay, what do we have? This is the first level, right? This is what's on chain. And what happens in a round transaction is that, you know, all of the people here, A, B, C, D, E, everyone is sort of like, let me just make sure I have the right one. Gonna use that one to be simple. So everyone that creates an on-chain transaction, right? Remember, we don't have covenants. So we need everyone that's involved in the round to co-sign that transaction. And so we have A, B, C, D, E, and all the way up to the server to co-sign that round. And then this is what it would look like. I mean, this is the UTXO that's going to show up on the average Explorer on mempool. But what's happening is that underneath, there's a bunch of leaves, and each leaves belong to individual users, right? And as you can see, hopefully, is that each of those leaves has those pending conditions. A plus S, B plus S. So it's every user plus the server. So those are all 2 of 2s. And what we can do, when I was saying we can do out of round transaction, what's an out of round transaction? Is, well, say I own this A plus S, what I'm going to do is that we're just going to co-sign and I'm going to add Charlie plus S here. So there's no new VTXO created until Charlie goes to the server and say, hey, I want to spend this virtual UTXO because I want to swap it into a new one in a new round where I'm going to put my signature. But as you guys can see, those are all just UTXOs. And so what else can we do with UTXOs? Well, we can do a script, we can do contracts, right? And so what's at the top of our mind, what was our first realization is, well, what's the most popular contract on Bitcoin? HTLCs, right? And so what if we're able to use Arc to do HTLC type contracts? And so this is why we decided, well, what's the first use case and the first go-to-market product that probably makes the most sense for Arc? It's to be able to help with Lightning rebalancing, right? We're doing virtual swaps, basically, right? So everyone's familiar perhaps with how Liquid, people have been doing that on Liquid. You hold some Bitcoins on Liquid, you swap your Bitcoins into inbound or outbound liquidity using a service called Bolts. And so we're working on an integration with Bolts that allow people to do the exact same thing, but in a much more trust minimized way than with Liquid having to trust a federation, right? And so the idea here again is, well, you just have virtual UTXOs and you have full control over those virtual UTXOs. But now, to be able to rebalance Lightning Channel, you don't have to make on-chain transactions anymore. You can just do off-chain swaps, and this allows you to massively scale your Lightning operation. And we think that's going to have a major impact on anyone that's a Lightning node operator, because obviously, like, we've changed the game completely in the sense that you don't have to incur all of those on-chain fees. Obviously, all of the virtual UTXO swaps are tied to an on-chain transaction, but what happens is you're amortizing that on-chain transaction across a potentially unlimited number of users. So swaps are probably one of the most interesting things that you can do with Arc nowadays. And one of the major reasons why that is so, again, is that we don't have to, we can create parameters around the Arc server that are much more convenient than with mobile payments, right? Remember I said 5-second rounds, 4 weeks expiry, but why do we need 4 weeks expiry? Because we need someone to come back online to make sure that their virtual UTXO doesn't expire. Lightning node operators are servers. They're always online. So we don't need to have such a long period of time for the expiry to happen. We can make virtual UTXO expire after 24 hours, but it doesn't matter. The server will always be there to roll over the virtual UTXO and make sure that it doesn't expire. And obviously, Lightning rebalancing does not require, it's very rare that you need to rebalance your channel like now. Normally, you can like prepare that in advance, you manage your operations, and so you can be a little more we can have rounds that are happening maybe every hour. So, the on-chain footprint is lesser, and then we can allow ways for Lightning node operators to coordinate around the best time to be making those rebalancing operations so that we maximize the amortization again of those on-chain costs. And so obviously that's very interesting for Lightning, but what else is this interesting for? Well, pretty much every single sidechain, layer 2, whatever you want to call it, that people have been working on. And so, I think there's a lot of people, especially people that are working on rollups and BitVM and things like that, that have proposed that most people are not going to be using the actual bridge, but are going to actually be swapping in and out of those systems, because those are the user experience around this is much more convenient and probably maybe cheaper even for users. But remember, why are we building those layer 2s? It's because on-chain is going to be expensive. So whenever a user wants to sort of like move out of this whatever layer 2 sidechain rollup, CAT VM, ZK coin, whenever those users want to move out of those layers, if the proposition is that we're going to have you swap on-chain, well, you're going to be paying an on-chain fee, and that's going to be pretty expensive down the line. And so what if actually you're just swapping out to Arc? And Arc gives you a virtual UTXO. It's as legit as an on-chain UTXO as long as you manage it, you don't let it expire. So we see Arc is kind of like becoming, and don't call it the only layer 2, but like we kind of like see Arc as becoming this sort of like intermediate sort of like interface for people to be able to move perhaps their funds in and out of those different layers without having to hit the chain. So you only have to hit the chain if basically you need to maybe like send funds to cold storage. And the same is obviously, if you're more familiar with Lightning, the same is true of Lightning. Like, you're managing your funds, your channel gets a bunch of liquidity, it becomes a little too fat, you want to remove some of that. Why would you put it on chain unless you want to send it to cold storage? Much better create a virtual UTXO, and that creates a lot more, this creates funds that are much more available for you to move around whenever you need them to without having to pay full on-chain fees. So, we think that this is, again, a use case of Arc that does not require like the gymnastics, and because we know that like dealing with mobile use case and payments like that, this creates a lot of headaches because, mobile phones are just, not always online, they're not reliable. And so payments in a way is kind of like the hardest use case, even for Arc. But there's a lot of things that we can do with Bitcoin that are not payments, and swaps are probably one of the most major ones. So we're really excited about this. And so, I mean, okay, well, looking ahead, like what else can we do? Okay, well, we have virtual HTLCs, we have virtual UTXOs. What if we can do like virtual like contracts? Well, we can do like, people are very interested in DLCs, for example. What if you want to build like a poly market on that's based off Bitcoin? Well, if you're doing that with DLCs, I mean, you're gonna hit the wall pretty soon. Eventually, if your thing scales, significantly, you're gonna realize that, well, because DLCs maybe is just like an escrow contract, right? You want to do escrow contracts on Bitcoin. I mean, that's cool, but that's going to become very, very expensive if fees are high. So what if you just do DLCs, but on Arc, right? Because there's no reason why you cannot create script spending conditions on all those leaves and make it so that you really never have to hit the chain unless you want to truly settle something. And so we think that's an interesting use case, and we're looking into collaborating with people to be able to build those things. And what else? Well, virtual channels. Obviously, people have been talking about that. The idea is, well, okay, sure, you can swap your liquidity around using Arc and get inbound or outbound liquidity. But what if you can actually start opening channels, on those leaves? Well, what if we can have this guy and this guy agree that like they open a channel together, and that gets branched out into the Lightning network? There's a lot of complexity involved there, And we think that there's something about payment channel, and I'm not gonna I'm not gonna reveal too much right now, but we think there's a lot of things about payment channel where they're probably very interesting even outside of Lightning. And when you do that outside of Lightning, you start simplifying a lot of things. And so why did we skip over payment channel originally? Well, the idea was, well, obviously they're very expensive to open on chain. So if you have to open single payment channel to everyone, that's going to be expensive. Now we can open channels off chain. So we think this opens up a lot of possibilities. And one of the things that I've been fascinated about is this idea of and this is probably not for everyone, but what about meta protocols? What about all of those runes and all of those ordinals and RGB counterparties? Those things are using UTXOs to be able to tag data into the blockchain and basically work off this network of indexers and nodes that are interpreting that data and creating other use cases, maybe assets and whatever, through that meta protocol. But obviously using UTXOs, again, that's not going to scale. It's going to be very expensive. People are building those constructs where you're doing those pre-signed Bitcoin transaction-based trades of runes and all kinds of other assets using the chain. And you have this slow-fi idea where it's okay, we have this meta protocol that's interpreting like a virtual machine, and you can call a contract by putting some data into your UTXO transaction on chain, and then that's going to create a swap with someone or whatever. But I mean, that's kind of that's cool. I mean, we love the fact that people are playing around with UTXO because we truly believe that UTXOs are much more superior to account-based model for decentralized finance applications. But the issue is that UTXO on chain, again, it doesn't scale. It's going to be very expensive. So, well, what if you have your indexer, instead of looking at the data that's on here on chain, what if your indexer is just looking at the data that's nested within the tree here? And then you can start doing all kinds of crazy things by having actual Bitcoin UTXOs, but sort of calling functions that are again run by meta protocols, so different set of nodes than Bitcoin, but that are looking inside the tree rather than at the top level. And so this is not something that ourselves we're going to build, but we think that there's a potential here for people to build systems that are very aligned with what they're trying to do already, but are much more future-proof and much more sustainable by using, this aggregation power that ARC has. And what else? Well, obviously, I mean, Covenants is one thing that we're looking ahead to. We think that, again, there's a lot of ways that ARC can be extremely useful today without Covenants. This is why we're building on ARC, because in a way, this is kind of the only thing really that we think is sustainable and has near-term applications, and we'll be able to actually ship production code with in the near future. And so, it's kind of it's stimulating in the context of these arguments about opcodes and whatever, but obviously Covenants would make ARC quite a bit better. And you would improve the UX, it would improve the efficiency of the system, and certainly the scale. And probably the most important is it would probably improve, so the worst case scenario. The worst case scenario is okay, what happens if the ARC server goes offline and everyone that's within that UTXO3 needs to sort of go on chain, right? Well, because there's, right, we have, so let's say these guys need to go on chain, they all have their unilateral exit. Well, I mean, this one, that's just that's a pretty small tree, right? We got 8 people here. But what if we have this, I think I have one here with 6, I don't know if it's even gonna show up, right? But yeah, okay, so we got 64 people here, right? So look at the level of transactions that are involved. All of these transactions, so let's say this guy here wants to go on chain, he needs to broadcast this transaction, this transaction, this transaction, this transaction, this transaction, this transaction. So every single transaction needs to go, so it's not like Lightning where you have to put only one transaction on chain to unilaterally exit. you need to put a bunch of transaction on chain to unilaterally exit. So that's kind of like the trade-off of Arc and any sort of like shared UTXO systems. Is in the worst case scenario, it can be pretty expensive. But obviously we designed those systems so that we incentivize, the operator not to go offline because they have really no reason to, because they themselves cannot cheat. They cannot steal funds from users. And even for them, putting those, all of those interactions with on-chain becomes expensive. But if we have covenants, maybe we can find a way to kind of like pull those VTXO out of the tree. Maybe we can find ways for all of these people to say like, okay, let's all bail together into a new arc, so that basically let's all bail together into a shared UTXO rather than our own UTXO on chain. So those are like super interesting things to explore. I'm happy to also explain what else it is that why covenants make Arc better. But the one thing that I would put emphasis on is that, again, obviously right now this runs off of Signet, but I was having arguments with my team about whether or not we wanted to do it on mainnet today, because we probably could. And I mean, Arc is a much more simple system than anything like Lightning. People will realize as they work towards implementing it, and we're trying to make it as easy as possible to implement, and it's going to be ready. At least the Arc node, which is what we're working on for the Lightning rebalancing, is going to be ready very, very soon. And so I want to encourage people to have a look at Arc again under this new light that is, Arc is not strictly for payment. Arc is this, don't look at Arc as this layer 2 that's going to make mobile retail wallet usage awesome, is going to solve all of Lightning problems. Maybe it will, but there's a pretty long road ahead for that to happen. But even putting that aside, there's such a big opportunity for us to look at Arc as this new construct that we can use to do multi-party contracts on chain, to aggregate any Bitcoin operation that your company might be doing. Are you just batching transfers or whatever? Are you doing, what is the potential for you to be doing swaps and whatnot? Are you interested in PSBT style, trading and whatever, if you're into that? I mean, we think Arc has a huge potential to improve the efficiency of all of those operations. So yeah, I mean, if you guys are interested in building on that, if you have any questions, we're going to continue putting out documentation and whatever. But please reach out to us, because again, this is something you can build on today. You don't have to wait for covenants. You don't have to wait for BitVM bridges. It works.
Questions? Is that Arcade that I see? The work?
Yeah, this is Arcade, exactly.
I have perhaps two basic questions about Arc. So the settling rounds happens every 5 seconds.
Well, it will depend on because that's the thing with Arc, right? That's why I hesitate to call it a layer 2, because it gives the impression that this. It's not because it doesn't have unilateral exit like Lightning. It does, and in that sense, if that's your standard for layer 2, that's a layer 2. But it's not a monolith like Lightning. Arc servers are just this primitive, this construct that you can use for all kinds of applications. So yeah, if you want to do payments, then yeah, the rounds are going to have to happen kind of in a very fast way. The interval will need to be short, right? Because again, you're trying to design for someone with great UX. So if the rounds happen every hour, well, oh damn, you want to settle the payment you just received. If you missed one, then it's going to happen the next hour, and the user is going to be like, well, no, I'm just never going to settle, right? But if you're building for example, for Lightning swaps, for rebalancing channels, again, you're dealing with a server here, so you can the server cannot miss a round, because the server is always online. So whenever a round happens and the server needs to be doing rebalancing, it'll happen, right?
I see. So when if I understood correctly from the original paper, so every settling round, needs to create a transaction that goes to the chain, right? So basically, if you're doing this payment use case, basically there will be rounds every 5 seconds, and then you will accumulate a lot of transactions that will have to read the chain when the block closes, something like that.
Exactly. So yeah, I mean, I didn't bring that up, but just, and this is kind of like orthogonal to the point you just made, but yeah, Arc is not a coin pool, right? Arc is not this single UTXO that we're changing. So like the distribution of the virtual UTXO within Arc is new UTXOs on chain periodically. And indeed, if you're trying to do payments, yes, maybe they'll need to be on-chain UTXOs consecutively very quickly, and that's going to create, yeah, if you're doing every 5 seconds, it starts adding up, right? But the most likely scenario is that a lot of Arc users or people that are building products targeted to payments with Arc are gonna have to find this trade-off of out-of-round transaction, right? A little more trusted, and full in-round settlement, which is when you get your true VTXO. So maybe, you know, if you're a merchant, you're accepting payments daily, maybe you don't go on-chain into a new shared UTXO every time you're receiving a payment, right? Maybe you're fine accepting the trust model where, you know, at the end of the day, you settle your balances, right? You receive a bunch of out-of-round payments during the day, and then at the end of the day, you batch this all into and this is probably better because you don't want to have, it's just like anything with on-chain or even with Lightning, you want to avoid having small amounts, right? You want to avoid collecting, not necessarily dust, but so the bigger your VTXO, the better it is. So maybe you're just batching that throughout the day. So, you know, there'll be different ways for people to use Arc as payment, but it's very, very, very unlikely that every Arc payment for that use case is going to go into an on-chain, a new shared UTXO, because then, yeah, it's just not going to scale. It's going to be actually too expensive.
There are no fees in your demo. How do you prevent spam or incentivize node operators?
Yeah, I mean, the only fees in my demo, actually, you're not gonna, you think you can see it. I sent, right, 5,000, and yeah, the UX is a little wonky right now because we did some change yesterday that I don't know if it broke some, but you can see, I think that's the transaction, and so yeah, the current fee right now that we're showing is just the anchor output that you need to put on chain for those. But sure, there'll be fees. The fees will be a function of basically the liquidity requirements for the Arc operator, right? Because the Arc server is fronting every on-chain UTXO, and so there's kind of like a concept of, and Peter Todd said that earlier, but there's a kind of concept of time value of money. With Arc, you're basically kind of like renting space into UTXO until you actually get to swap it to someone else. But also the fees will be a function of how many people are joining this round with you. When you're settling and you're creating a new shared output, obviously, the more people there are in that shared output, the cheaper the on-chain fees for everyone. If you're creating a shared UTXO, but there's 2 people inside the shared UTXO, well, you're just splitting the on-chain fees between 2 guys, right? But if you're doing this and you have 64 people, a single on-chain UTXO and 64 people, then that starts being really, really interesting, right? But yeah, obviously that's a way to incentivize the server as well. Yes?
Like a question. I think you mentioned earlier, I don't know if my brain didn't catch it, like what happened if your network goes down, how do you process?
You can repeat the question.
Like,
Yeah, so the question was what happens if the network goes down, right? So again, I'm just going to nitpick a little bit, but there's no such thing as like network and it's not like Lightning, but there's a server. It's a client server implementation. What happens if the server goes down? Every person, I mean, let's say it goes down and never comes back, right? Well, every person here needs to, every user that owns those virtual UTXOs as a transaction that they can put on chain to be able to retrieve their Bitcoin, right? So those are all pre-signed transactions. They're valid, they exist, and they're confirmed on chain. And then every user say, hey, I have this 1,000 sats in ARC, and they just publish that transaction on chain to be able to get their funds back. But the tricky part, as I was explaining, is like, if you're in a big ARC and there's a lot of people, again, it's not like Lightning, because you need to put every transaction, ancestor transaction, to yours on chain. Meaning, you know, here we have like how many levels? We have like 6 levels. So you can put like maybe like up to 5, 6 transactions on chain. So that's expensive. So that's the worst case scenario. You don't want the server to go down, but I mean, things happen, but it's like, you know, it's obviously like, probably it's gonna happen, maybe eventually, but again, the server has incentive not to, like, why would the server can come back online? Yeah, maybe sure, like there's some DDoS or whatever, server goes down. Maybe he can just come back online. Again, there's no state here, so it's a lot easier to kind of like have the server be back online than like some like things like Lightning where you have backups and all of that stuff. But generally speaking, yeah, you want to incentivize, the server is making money. So ideally, unless like the government goes and say like, well, shut your thing down, the server is kind of like incentivized to come back online as soon as possible if he does go offline.
I'm going to wrap it up there. Alex, thank you so much. Last work we find ARC and you.
Yeah, arclabs.to. Check out the ARC node. Again, is going to have like a beta or alpha release pretty soon for anyone that likes to play around with Lightning, especially if you're operating Lightning nodes, you're balancing channels and all of that. Right now we're supporting LND only, but like reach out to me if you're interested in that. This is going to be very simple to play for you to play out, and you'll be able to probably realize the power of ARC very quickly. Otherwise, arcdev.info as well. If you want to look at some of the documentation, it's not perfect yet. I mean, my next step after this sort of like conference roadshow I've been on is to like overhaul and revamp a lot of that stuff. So yeah, thank you guys.
Lunch is open. We have a shit ton of food in the cafeteria back here. If you go, you turn right, you'll start smelling it. From Al's down the street, bunch of sandwiches, salads, got the range of dietary preferences, and we have 45 minutes, and at 1, we have the next presentation. But we also have Bitscript. Jesus over here. I think we'd said you were going to be in that room, but like the cat thing's still going on. I think it is, yeah. So kind of up to you. Where do you want?
I'll do it here. It's much more workshop oriented.
Okay. Otherwise, go.
So that one.
You could just make a call.
All right, we'll do the other one.
Okay, we'll do the other one. But otherwise, we have a ton of food, so don't be shy. Otherwise, thanks y'all. Thanks for coming.
It's here. It'll be right after. That's next after lunch. Yeah. Let's go.
Yeah. Your call.
Recording stopped.
Oh yeah.
And the server. Really, like you're trusting the server. Yeah. You're trusting that the server doesn't allow.
the other day. What is this thing?
Some of you have seen this preso like already or something. Don't be harsh. We don't have a designer. It's just like whatever. So we're waiting for more, or like just we can.
I'd say kick it off. This is also recorded so that
Okay.
we can.
All right.
There's
Go.
a couple hundred people watching this talk.
All right. I wanted to get Louis to write about this, but whatever. So I know that some of you guys have heard this thing like already a couple of times. Sorry for this, but like whoever wants to just stand up and leave like because you've heard this already, please do. But like it's not going to be a bad thing, whatever. But for those who haven't heard this, there is this paper about Bitcoin pipes we have put together like whatever, about months ago at this point. Like since then, we kind of just ran around for reviews, for feedback, for everything. I mean, if people have something to say about it. And so what's the point of that is that, apparently we can pull off like covenants on Bitcoin. We can emulate them without the necessity for a soft fork via, pulling off predicates for functional encryption. So that's like the thing. Oh, Louis, I was waiting for him. I was waiting for you, dude. Where you were?
I'm so sorry, but there's a guy also.
So, all right. Now everybody's in there. Now everybody's here. So, all right. Apparently you can do this. So yeah, like what's the problem? Like how this whole thing like kind of started? All right, we kind of put together this, provable stack for over the last like 8 years. And I was like, okay, well, how can we make it applicable to Bitcoin? You can't really verify anything in there. You can't verify ZKPs or anything. You don't have covenants. You don't have like opcodes, FCAT, opmule, just forget it, never gonna happen. Like missing opcodes, opstark verify. Dude, come on. At this point, opstark verify. That was a good idea. That was a good proposal. Unfortunately, well, I can't see like whatever. ZKP verify also. Block size also limits us from like kind of putting in large proofs in there for like just verification, straightforward verification. So yes, I know block size works. We've been there. Like forget it. I'm not pushing anything in there. So protocol upgrades, as I said, forget it. Verification methods. In fact, yes, you can pull off some verification with BitVM. Sure, it's going to work. Interactive, somewhat optimistic. You can try to pull off the soft fork if you really want to, like, if you like hunt down every single miner in the world and like, kind of point a gun at them or like make them upgrade. And maybe after that they will upgrade, but like, feel free, like, good luck. So what to do? How do you verify ZKPs on Bitcoin? So you can try to emulate these covenants because like, what the hell covenant is? Basically, it's whatever. You gotta put like some additional conditions on what kind of transaction and like if the transaction can go through into the protocol commit log. So that means kind of how you can spend your Bitcoin of like whatever. So in the end of the day, emulating that, the closest way to achieving that is to kind of try to what's another way to do that? Like usually how people do this, they use pre-signed transactions or like they encrypt these pre-signed transactions and try to decrypt them like after some condition is met. Like the oldest trick in the book. Like, what if you, in the end of the day, what if you don't decrypt anything? Like, if you, for example, like encrypt the key and you never decrypt it, so you kind of try to get that thing signed without decrypting actually the key. So sounds something like FHE, but like not really, because with FHE, in the end of the day, you will result with decrypting the private key anyway. So how do you not decrypt it? Well, there is this like semi-forgotten notion. There is this like semi-forgotten field, like or area, like functional encryption. Not like semi-forgotten, just underdeveloped, right? But and the nuance with that is like the idea in there is that you can basically get the ciphertext. You can like define some functionality you want to like execute over the ciphertext during decryption. I mean, kind of like a functor, like a lambda closure, if you want to call it that way, like an analog. So, and in the end of the day, you result with kind of executing some computation over the encrypted data without actually decrypting the data and getting as an output only something which is kind of the result of this computation. So, and like formally speaking, you can emulate the counting with it. I mean, because you can encrypt the private key, cool, kind of inscribe the ciphertext just to store it like somewhere in Bitcoin ordinal style. I know, guys, you're gonna tell me that I'm like spamming Bitcoin again. Like, sorry, I'm not. But you can not inscribe it. You can store it whatever you want. But anyway, so generate all the decryption keys which are relevant to like functionalities you want to execute over the ciphertext, and then whatever, like perform these computations. Basically, generate the ZK proof for them, put the ZK proof into the decryption functionality, and like if basically the verification within this decryption functionality happens correctly, cool, get your Schnorr signature over the data you've put as an input in there. So theoretically, that's the framework, that's the blueprint, right? How in particular this could work? Because like, let's be honest, functional encryption, general purpose functional encryption is not practical. It's underdeveloped, like really underdeveloped. So that's like the overall like, I don't know, workflow, whatever, just what I described. So now we're gonna get to a little bit of whiteboarding, right? Let's go for it. Like, if you wanna like see anything, please come closer.
Go grab the microphone.
Wait.
Oh, grab the handheld microphone, I'd recommend.
This one?
Yeah.
All right. So can I just
turn it on?
That works. So what's the problem with general purpose of feed, right? How usually it's being done? Like usually what you get is like you define some like function which like gets you from like one thing to another, and like this little f which you have is defined as like some kind of circuit, which is, I mean, like whatever, like general purpose circuit, right? So in the end of the day, what's the problem with this is that if you encrypt the private key, you got to make sure that it doesn't leak. So if it doesn't leak, like if you want it to not to leak, then you gotta like somehow either hide it within the circuit, which means you gotta do indistinguishable obfuscation. So what does that mean? Is it means that you gotta define this circuit the way, so brute forcing through all the possible options, like for input and for the output, would be easier than to try to figure out what's hidden inside, like than to try to like kind of figure out what the hell this circuit is about. So this approach, I mean, there are schemes which implement that. Those don't work, right? I mean, they work, but it's not practical. I mean, it takes you like several days, like to just whatever do one round of like AS, and it's not really secure because those are multilinear maps based. Multilinear maps, no matter how hard Dembanet tries to convince everybody that he fixed them, well, he did not. Like, sorry. So that's what it is, and. What to do? It's like, again, there are functional encryption schemes which implement some kind of like function hiding properties, but over a very particular functionality, like over a very particular function which defines like not just general purpose circuit, so you could basically define whatever, but some particular functionality which is like some multiplication, whatever, let's say, right, for simplicity. This way. So just the multiplication. And if you do just the multiplication, you can keep the basically whatever, like ciphertext hidden, whatever. I don't know how to denounce that. Whatever, hidden, just hidden. And you can also like keep like basically all the data you try to operate over hidden as well. The problem is the functionality is limited. So what to do? It's like, again, what if, it's like, what in particular, this, like, you know, the family of these functional encryption schemes, I mean, it's usually pairing-based, like billionaire pairing-based ones, and like those are which are most functional ones are DPVS-based, double pairing vector spaces-based. So they achieve the function hiding property by basically decomposing the ciphertext and like the decryption key to two bi-orthogonal vector spaces. So you can't really figure out what the hell like in there until you multiply them. And once you multiply them, well, you got the result. You still didn't figure out what the hell is in there. So that kind of, it's the way they keep the function hiding properly. So, so what if, like, in the end of the day, you can stretch a little bit this functionality you can do over the PVS framework and basically try to compute something more complex than just the linear functions effectively, because, like, you know, pairing is just whatever. You can embed some linear functions in there, kind of, you know, just do different multipliers, like Z, A, B, C, whatever, like any amount of them. At the end of the day, it's going to all become like just a linear operation, one linear operation, whatever, nobody cares. So what if you can stretch a little bit these things, like this functionality, and try to make it work over a little bit wider set of polynomials, right? So there are attempts to do this as well. Pretty recent one, actually, like 2020, 2022, the paper of 2020, 2022. So there are attempts to make, and like, you know, even the results on how to make like QFE schemes, function hiding QFE schemes, which support not just linear equations, but they support quadratic equations. Should be enough for a certain type of computation. Definitely not for everything. I mean, like, it's still not a generic purpose of E. So what can you fit in here? Can you fit what we need from that? Like, and basically what we need to emulate the covenant-like functionality is we need to emulate the signature, like it's Schnorr signature, right? Why Schnorr signature? We'll come to that later. And like we want to, like, since we can't put a lot into quadratic equations, we can't put it in there. We gotta emulate, we gotta put in there the verification most probably of a ZK proof, which would be generic enough for you to be able to pre-compute something, generate a proof of that, verify that. If the verification is correct, you get the signature. Cool. So can you? And the answer is apparently you can. I mean, like, apparently you can arithmeticize Schnorr signature the way, like, so you could emulate the non-native arithmetics over like BLS or like any pairing-based curve. So like bit decomposition and like trick, and so like basically decomposing the whole Schnorr signature signing process. What is it like? A hash, couple of additions, exponentiation, and one multiplication, right? As far as I remember. So can you decompose that to non-native arithmetics operations over pairing-based curves? Yes, you can. I mean, like bit decomposition style, R1CS bit decomposition style. Not really, but, you know, similar way. So another question is that what kind of proof system can you prepend to this Schnorr signature, to Schnorr signing, so it could fit the DPVS framework? Like, so it could still be like pairing-based one. I mean, sure, it's some kind of like IPA-based one. It's for sure not a hash-based one, unfortunately. I mean, I'd love that because placeholder is like the proof system I designed back in nil is like hash-based one by default, but like it's pairing-based one. Pairing-based one should fit. Like, I mean, instantaneate KZG-based proof system with Blankish arithmetization over BLS curve, you can fit the verification of it into the, it's like you can express verification of it like through QFE. So, I mean, like, again, R1CS style, like people have expressed this, people have wrapped the verification of like different proof systems in Groth. They've done it once, like just do a little bit of a reverse process, doable. So in the end of the day, what we result with basically Schnorr, like QFE arithmeticized process of Schnorr signature generation over non-native arithmetics, emulating SecP curve arithmetics over a pairing-based curve, multiplied with like some IPA-based proof system verification, also embedded natively into pairing-based curves, and kind of, you know, you can't decompose it to QFE in the end of the day because it's all pairings. So you result with this. And like in the end of the day, if you don't get the verification correct, and it's basically zero, then you get like no Schnorr signature out of it. So this way you could kind of emulate generic purpose predicates. Emulate, it's not the general purpose predicates, for sure not. But you can emulate that for this particular purpose, for emulating covenants. And it depends on which circuit you define in here. That kind of particular covenant functionality you can, you know, result with. Like right now, it's pretty obvious that we can do stateless covenants with this. I mean, we can do, well, guys, you're gonna hate me, like concatenation, we can do this, that's like for sure. We can do CTV with this, that's like for sure. We can do, again, anything which comes up to mind which is stateless, which doesn't require like introspecting Bitcoin's L1 state. This you can do. like, can you do stateful covenants with this? Well, you gotta prove like the state inclusion, something that you can define a circuit of it, like probably, but it's a different conversation, right? How can you do stateful covenants with this? Stateless, right away out of the box. Stateful, I don't know. So that's the overall process, how it is kind of practical. So in terms of like performance and everything, so I mean, there are different methods of like trying to enforce those covenants that are like, you know, kind of, whatever. Even, okay, well, since Louis isn't here, like you want to talk about like practicality of hash collision-based covenants? So because there are also questions about practicality in terms of like performance for FE-based covenants, and it's not going to be seconds like per each spent. It may be not going to be even like minutes per each spent. I mean, it's like we do like, I don't know, if we do less than an hour, like we're good already. Like we're already like, you know, like that's a win. So that's what it is. But in the end of the day, like, I mean, come on, arithmetizing like Schnorr signature, even hash arithmetization in there is going to take like, 60,000 plus equations. So you will result with like basically this matrix containing like 65K plus equations in here just for the hash. Like exponentiation is going to be also rough because it's, because what the hell is this? Whatever. So arithmetization, exponentiation is also going to be like rough because you would be required to emulate non-native arithmetics, non-native SecP arithmetics over BLS. So that's also going to take something like not less. So in the end of the day, you will result with like just two big ass matrices requiring to do a lot of pairings like with each element of theirs. But you know, doable. I mean, it's like doable. Doable. Yeah, I mean, it's like we're just working on the implementation, so it's like I can't really say like the benchmarks or something because we just don't know. It's just like theory, and we're like working on implementation. That's it. So that's like I guess what it is, and like let's go with like Q&A or something because I kind of apparently skipped half of the thing. So like just do it.
Questions? Where did I put the microphone? There, yeah.
Yeah, it's in bar.
If you want to ask a question, get Fred to hand you the microphone.
Oops.
Who wants it?
Yeah, let's go.
I'm very dumb. So at the very starting point is, can you sort of explain the intuition about why this FHE algorithm, I mean, how it works? Because I didn't get the intuition, and I just sort of why it works and how it's like fits together, because I honestly didn't capture the reason. Yeah, like the intuition, I don't need the math, like just like, sort of like high level.
High level picture. Yes. Let's go again, high level picture. So high level picture is like, we do understand how do we get, for example, like inner product from whatever pairing based FE scheme. So you can only like compute inner product over ciphertext, right? So that's like what it is. It's a limited functionality. I mean, you can't get anything else from like ciphertext. The trick in here is how do we extend that? How do we extend it? How do we get a little bit more than just inner product over the ciphertext? So like high level picture, how do we get inner product is before we go to decrypting something, we split the setup, the whole setup, like with ciphertext, the decryption key and everything to basically two bi-orthogonal vector spaces. And we just do like a lot of pairings with it. It's like with each of the elements. So in the end of the day, you result with just computing just the inner product. Cool. Can you do a little bit more? Yes, you can. If you turn this from just kind of linear equations expressed inner product to quadratic equations expressed, like QFE basically. QFE attempts, like we did some attempts. There was whatever entity labs results in QFE. So you can express some computations which are possible to be done, which are possible to be arithmetized as in quadratic equations within this predicate, right? So the question is then, can you arithmeticize the Schnorr signature or the IPA-based persistent verification in this set of basically just QFE, basically equations, right? Can you arithmeticize that in there R1CS style? Yeah, the answer is you apparently can. So, and this what gets you to emulate general purpose counts.
So I mean, another thing question, because I mean, I have to admit, it doesn't really help me because what I don't understand. So for assuming, I'm going to assume the FHE works, there is some form of FHE that works, but how does it relate to the state of Bitcoin? How do I get, how do I constrain the covenant? That's the whole point. I just don't understand how anything can relate.
I see. Okay, so how does that relate to Bitcoin at all?
Yes, I mean, how do I condition basically my covenant?
Yeah. Okay. Basically, what makes this a covenant is the embedding of the Schnorr signature generation within this predicate. So that's basically what makes it relevant to Bitcoin. In fact, so only the fact that you generate a Schnorr signature instead of just inner product, you generate a valid Schnorr signature as an output, gets you basically this thing to be relevant to Bitcoin.
Can you say that again, the microphone?
Yes.
Yeah, this way. Let's do it this way. So just the fact that you generate the Schnorr signature instead of inner product as an output of the predicate execution makes this thing relevant to Bitcoin. Because
So, okay, so basically I'm doing a trusted setup. So I'm hiding some keys.
Yes.
And now I do some operation, general purpose operation, which inside this FHE.
FE. Just
sorry.
Yeah,
So
FE, not FHE, FE.
Yeah. So if you're trying to understand high level, so you have this trade setup. So I'm going to hide this key.
Yes.
Which is going to serve as confidence.
Yes.
Okay. So this key is hidden forever.
Yes.
Everyone burns the key, whatever. It's hidden there. Okay. Great. So now, what you're saying is that you have a method, which I didn't understand the mechanism, but that's mostly relevant if I think about it as a black box, which says I'm going to operate some verification, some set of compute inside this black box, and the output is going to be a neutral signature that enforce some requirement on the covenant. Like it would enforce some requirements on the message.
I mean, it's you either get the signature of that message, either you don't. And the condition of it's the condition enforcement or some spending condition enforcement happens not on Bitcoin on one inside Bitcoin script, outside of it. And if it's satisfied, you get the signature for whatever data you've put in there, which is the transaction. So if it's not satisfied, you just get nothing.
Okay. So let's assume that, for instance, this computation is, let's say, a snark, whatever. Let's say it's a snark. So I can enforce, obviously, arbitrary program because it's general purpose verification environment. So what you're saying is that you have a method that, assuming some hidden private keys, if that is trusted setup, can run a start verification inside that protocol and output a signature that's a valid signature on a message that is produced by this black box.
Yeah. I mean, it's
so how is that not general purpose FHE?
It's FE, not the FHE.
FE, sorry.
Yes. How is that not a general purpose FE? It's not general purpose FE because you still can't do general purpose predicates in there because it's not circuit-based FE. It's the extension, it's the stretch from inner product encryption, which usually results you with only one functionality over the ciphertext. Inner product, that's it.
Okay,
Nothing else you can get.
So there is one, so it's not general purpose, so I can just do inner product. So what can I enforce as predicate if I only can do inner product?
Here go, it's now you can't really enforce a lot because you can't express Schnorr signature within linear equations. So this means you can't really compute it, you can't really make this inner product to be a valid Schnorr signature. But it's you can stretch this a little bit to become QFE. It's
Q stand for?
It's a quadratic functional encryption for quadratic functions. So it's a little bit large, a little bit wider class. Cool. And the question is, can you embed the Schnorr signature into this class of functions? Can you express that? And like, can you make it like, a valid Schnorr signature? So the claim is you can.
So if I recompose, basically you are hidden private key, burn for the word.
Yes.
I can put some very limited compute, which is like here a short signature.
Yeah.
And I'm going to be able to extract a new signature from that, from that system that is valid based on the private key. So no one knows the private key, but I extract some signature. So I do not see how that's a covenant because it doesn't enforce any predicate on the message.
Yeah. I mean, like just it's like screw some proof system verification before the Schnorr signature. We're talking just about the Schnorr signature predicate right now. Like,
right.
Screw that.
So I'm just allowing to sign the message without knowing the private key
on your behalf without revealing the private key. Yes.
So how is that just not something similar to like blind signatures? So why is it not a blind signature system? For those who don't know what's a blind signature, is that I'm signing, you're giving me something, I'm signing it, but I don't know what I'm signing. So how is it not a blind signature, which is not governed?
Well, it's like for blind signatures, you gotta set up like the whole scheme. It's not. It's interactive.
Right.
So this case is not interactive.
In terms of black boxes.
Yeah.
How does that condition any next pending condition? I do not see. I can imagine. Okay, I can imagine a blind signature scheme, like a form of blind signatures. I just don't understand how it predicates.
Okay.
It conditions the pending condition.
Okay. How it can be conditioned? It's like the condition comes in when you put in the proof system verification. Like again, embedded into QFE, expressed by a QFE before before the Schnorr signature generation.
Still unclear, but I don't know if you have more questions. Like I'm not going to take all the mic.
I mean, we can go through that. I'm down. Yeah, let's go. I'm down.
Okay.
Okay, so my question, thank you so much for the presentation. So how would it affect the transaction fee? Would it reduce or add on to the user? Second question, like, what is your kind of like process or thinking in terms of the processing times? Like, how would you handle like network congestion like in the future?
I see. Well, it's like regarding the user fees and everything. I mean, it's like there is this nuance that this kind of method it either gets you the signature of the transaction you wanted to put in or not. So like whatever the transaction you formed, this is exactly what you're going to pay for it. So it's like it's on you to like kind of you put the transaction to one like whatever you define that inside the transaction, that's what you're going to pay for. So formally speaking, the added cost of this thing is it's just a signature verification, right? It's not really an added cost. So that's like the thing.
Zero cost for us?
Well, it's just a transaction. Yeah, I mean, you get the transaction signature. That's it. There is no like added cost on this thing. Like the downside is that you can't really understand which transaction came from like a pipe and which transaction came from like an actual user, because it's all going to be like from Bitcoin on one kind of, it's going to be the same perspective. It's going to be the same thing. I mean, like just a transaction. That's it. So that's like the downside of this. I mean, that's the first thing. The second thing, the second question of yours was more about like, how can this, I mean, kind of, increase throughput and something. I mean, let's say it this way. I mean, it's like, it can be used as the way to verify like ZKPs on Bitcoin. So like whoever does the ZK rollup, whoever does the L2 from Bitcoin, that's their job to like kind of scale this up. And this mechanism is basically just to make sure that, these L2s, these like rollups, the side chains, whatever, become like actually secure and become actually verifiable, and not just kind of optimistic or something like, hey, we're gonna slash somebody or whatever. No. So that's like just a verification method, I would say, for them. So it's actually like L2s, rollups, side chains, whatever's job to scale this up, I guess. I mean, I'm not claiming here to like increase the throughput of Bitcoin. So like, there is no claim like this in here.
Misha, thank you so much. I'm going to wrap it up there.
Okay.
We updated the schedule on the website so it now accurately reflects what the the afternoon looks like. So you can now go to Op Next. We updated the schedule up so you can go to Op Next for an accurate timestamp of things. So Rindell's over next door right now doing dev tooling post covenants. We've got Hunter on his way up to talk about one of the more fun topics, I think. Is it pressing? Is it urgent? Is it far off in the distant future? I'm going to let you answer that.
Yeah. I've got answers.
Okay.
Yeah.
He's thought about it.
Definitely thought about it.
Do you think you'll be presentation Q&A focused? How do you think?
Well, it's going to be a presentation, but if we have enough time, I would love to do Q&A. If we don't have enough time, then we can just go up to floor 14 and continue any discussions there.
Cool. Right. If you want, you can switch to that, whichever you want.
Okay. Oh my goodness, this is a mess.
I'll move this for you.
Thank you.
Should automatically pop up.
Hey folks, I'm Hunter Beast, and I'd like to talk to you about Bitcoin's quantum security. So you might have heard about quantum computing and how Bitcoin might be vulnerable to quantum computer. It poses a risk to Bitcoin because there's two ways that it poses a risk to Bitcoin. One is through mining, but mining is actually pretty impractical to do with quantum computers right now. Actually, just about everything is practical to do with current quantum computers. But what's even more low-hanging fruit are signatures. One thing that you can do with a quantum computer that is probably the lowest hanging fruit, like kind of like the one of the more viable things you can do with a quantum computer right now, is factor number. And this is using an algorithm called Shor's algorithm. And what Shor's algorithm does is it dramatically speeds up the capability for a quantum computer that is potentially slightly larger than what we have commercially available right now to be able to potentially derive, say, a private key from a public key. Public key you can think of being a very large number, 256 bits, in fact, and the elliptic curve behind that is called SecP256K1. That's used in Bitcoin. So when you have a public key that's exposed, a quantum computer could potentially derive the private key from it if it was powerful enough. When are keys exposed in the Bitcoin blockchain? So the first would be early addresses, because they're called P2PK or pay to public key, and they encoded an entire 65 bytes public key plus like a couple opcodes to check it, and that is the entire encoding of the entire public key, available on the blockchain for all time. Also, if you use an address to receive Bitcoin, and you spend from it, and then you use that again to receive more Bitcoin, then what you've essentially done with your first transaction is you've revealed your public key whenever you go to the mempool. In particular, all mempool transactions except for the one I'm about to propose is vulnerable to this kind of attack. And also taproot addresses, it's worth noting, is a 32-byte EXO-only public key. This is still just as vulnerable as a 65-byte public key to quantum computers. Now, Shor's algorithm, it's actually, like right now, it's pretty weak. Like people are like somewhat concerned about it, but it is making progress. What's interesting is that the results that come back from it are essentially kind of random looking. Like that chart on the right is like about the best it can do. And that this, the circuit kind of in the background there is is only good for factoring a number up to the number 15. So one question you might have is how soon might this be like an actual legitimate concern? And the answer to that is difficult to provide because I'm not clairvoyant, but what we can do is we can survey what's out there. And right now there's a commercially available piece of hardware called the Quantum System 2. It is capable of 133 qubits per QPU, and it can scale to many more qubits depending on however many systems you're capable of connecting. And there's a number of different companies working on this as well. There's billions of dollars being thrown at this problem, and as you can imagine, with early Bitcoins being sort of a potential incentive, there might even be more companies that'll be coming in and trying to see if there's any opportunities there. And this is actually an example. So this is the Quantum System 2. This is what it looks like. It's kind of imposing. A lot of you probably haven't seen a quantum computer. This is essentially what it looks like. It has a dilution refrigerator inside of it. It cools to colder than deep space, and it isolates the chips from RF and radio frequency radiation, thermal radiation, all sorts of like vibration and things like that. And this is on the inside, they have these like coiled wires because it's supposed to contract the metal because it gets so cold. And you can see the chip on the bottom there. So Peter Woolley, you might have heard of him. He says that sufficiently powerful quantum computers are hypothetical, and if they happen, there will be a long series of incremental breakthroughs. And what we've seen since he's posted this tweet in 2019 is a long series of incremental breakthroughs, and it's potential that we'll see many more. It's very likely, and so there's actually like somebody has actually put thought into what a quantum emergency might look like, how this order will occur, and there's it really just depends on the level of risk people are perceiving, and of course there are actions we can take to mitigate against that. Additionally, if you want to know the government's timeline for when they want to be prepared for quantum computing, it's around 2029 to 2033, as you can see here. One thing to know is that about 4 million there are about 4 million public keys on the chain. Well, actually, no, I should rephrase that. There are about 4 million Bitcoin that have their public keys exposed. And that's about 20% of the supply. This is according to a Deloitte report from 2020. And we've also adjusted for the additional supply since then. So what do we do? Well, we introduced post-quantum cryptography to Bitcoin. And right now, we're using SecP 256K1, and we have two implementations of the signature algorithm, ECDSA and Schnorr. They have their different byte sizes, but to give you kind of a comparison to some of the most modern post-quantum cryptography, and I'm talking about this is from just last year, SkiSign, which is considered kind of the state of the art for quantum computing, and it's not also fully verified that it is secure, is a size of about 335 bytes, and that's for the least secure version of it. And then there's also another one that's been approved by NIST, the National Institute of Standards and Technology, and that is Falcon, and it has public key and signature pairs that are about less than 4 kilobytes in size. But compare that to Schnorr, which is 32-byte public key and a 64-byte signature, we really do have this luxury of having elliptic curve cryptography still secure because it is so much more expensive to sign and provide public keys for any kind of transactions you might do using post-quantum cryptography. I represent an organization called Surmount Systems, and we have been working on a series of BIPs, P2QRH being one of them. This is for quantum-resistant addresses, and I'll go into that BIP shortly. There's also 2 other BIPs that we're planning on. Qubit activation, which we're thinking very hard about, which is the name that we've chosen for our soft fork. And also quantum secure addresses, which is a much further possibility for us to investigate. But ideally, we use quantum computers or something like them to secure, to sign Bitcoin transactions, and then you can verify them classically. And we were actually, so I've actually created a BIP and submitted it to the BIPs repo, Bitcoin BIPs. And it was covered in Bitcoin Uptake newsletter 307, if you're curious. There's also some audio version of some discussion around it. If you so write down 307 if you know bitcoinuptake.org. And then we're at Surmount Systems, we're actually working on a indexer we call Gabriel. And it essentially keeps track of what we call Satoshi Shield. And so there's essentially 1 million Bitcoin that were mined by somebody who looked a lot like Satoshi or could have been Satoshi, according to what's called the Patoshi pattern. If you ever want to look that up, it's a very interesting story, and we'll see. But what we're doing is we want to track how many pay-to-public key coins are out there and whether they've been spent or not. And it's kind of like not only just an early warning system against potential compromise of what's called the elliptic curve discrete log problem, but which is what secures elliptic curve cryptography. But it also is a sort of shield against potential theft against what you could probably just call plebs, because each address from early Bitcoin mining rewards were 50 Bitcoin each. And what's interesting is early Bitcoin Core clients, even like 0.1, supported addresses that started with 1. They were hashed, public key hash, but it defaulted to, when mining, pay-to-public key, which is a very interesting choice, design choice, if it was a choice, for the default version of Bitcoin. So people who might have forgotten or lost their keys or something, they also sort of contribute this this shield, to the shield that helps anybody with less than 50 Bitcoin in their address to be sort of at least crypto-economically incentivized to not worry so much during a quantum emergency. And that allows you to transfer your wealth to P2 quantum resistant hash address type. And this is an incomplete set of results, but it gives you kind of an idea of where things are with P2 public key. It's probably really tiny, but what it leveled off at is around 2 million P2 public key coins early on. And that's those are essentially the preliminary results from the Gabriel indexer, where we implemented the capability to read block.dat files and go through them and see if they've been spent, those coins have been spent. Now, to get further into P2QRH, because this is a Bitcoin workshop, plenty of Bitcoiners here understand UTXOs and how they're accounted for. And so I want to go a little deeper into that, if we have the time. And with Qubit, we want to introduce 4 signature algorithms. And this is a sort of redundancy in case one of them is compromised. And we also want to give people the option of having, these other quantum algorithms that are smaller in size, like ski sign, which is more experimental, it's newer, but it's also a lot cheaper. And so this gives Bitcoin users a lot of choice. It does complicate the lives of wallet devs and just most devs, really, because you're supporting not just one, but a total of 5 different signature algorithms. And you might even say 6 if you're including a distinction between ECDSA and Schnorr signatures. And so but the good news is that this is a soft fork. It's just a new address type for people to opt into. It would be essentially an improvement on Taproot. It might not be fully compatible with all Taproot programs, and we'll go into that in a bit, but basically we're keeping signature public key pairs in a separate field in the transaction we call the attestation. And this attestation would, you can see on the lower left there, that's essentially how a transaction is made up. You have the version, the marker, the flag, which in SegWit v1 is 01, and right now we set the flag in P2QRH to 03. And alongside the witness, we have this separate field called the attestation that we want to include only valid signatures that are valid for spending those inputs, and then provide a 16x discount to that because the signature sizes are so much larger for post-quantum cryptography. There will need to be a sort of discount in order to include the same amount of transactions or similar amount of transactions per block. And this will effectively increase the chain growth rate, but it is not necessarily an increase in what we consider the block size, because it's kept at 1 million bytes. It's just some of these bytes are discounted. Not all bytes are fungible, apparently. And so this is kind of the reasoning behind the 16x. Value is that we we thought it was a good balance between all the stakeholders. So we have to kind of convince, this is relevant to one of the talks earlier today, but we have to convince a lot of people that this is a thing that needs to be done for Bitcoin. And we've thought a lot about, individual node runners who will be probably the most impacted by this because of the increase in chain size and chain growth rate. We kept it at 16 instead of putting it to something absurd like 128, right? And so we could have made Bitcoin transactions much cheaper and this post-quantum cryptography almost free, but we didn't because it's important that this is priced in a fee market in a way that's at least appropriate but balanced. And not everybody's going to be happy with these compromises, but that's the whole point of compromises. Not everybody's happy, but it's good enough to keep Bitcoin secure. And we also have to convince enthusiasts, investors, all these other people, and come up with a soft fork and build utilities and tools for services, wallets, and layers. And also, a new development since, say, the SegWit era is that miners can now pick their own block templates, individual miners. And so if they find the magical nonce that allows them to achieve the difficulty required to mining a block,
that's something that we should evaluate,
they
because
will
I
be able
think
to
as Bitcoin
potentially
gets bigger, as we get more developers,
decide
we're going to
whether they
want
want to
higher level
support this
abstractions, we're going to want
in any kind of activation
and
scenario.
pick it in a library somewhere, so we want
Ju-
instructions that are
at a level that,
I think that we should also
ordinarily
be
mining
thinking
pools
about
were
what are
kept at.
the trade-offs
And
around
so,
operational overhead, data, cost, all
this
these
is
things
this
that
is
some of these
essentially democratizes
this is not
in
a
many
talk
ways
about
the
grinding, you know, like
activation
SHA-1
of a soft
and,
fork, and
right
it
on B
also
hashes, but, like, you know,
makes it
it's
so
a
that
consideration.
we
Like,
have
not
to
all of these
convince
things are actually
even more people to adopt
I've been mostly talking about a
P2QRH.
tool that we've been working on. We've been building this tool to
So
handle our
if you
use
think
cases,
that any of
and
that work is valuable,
think and I hope that it'll be
we
generally
are
useful for
working
other
really
people,
hard,
or that there's
and
gonna be one little
we'd love to
nugget
come
in
to more
there that's
conferences
useful
like
for somebody
this.
else and they go
If
build
you'd
something
like
better
to
with
go
it.
to
But there's lots of other really,
sermap.systems,
really smart
you
people
can
in
find
the space who have been working on other interesting tools for a while to try
some
to pull
payment links for and
complex
contribution links
contract
for
authoring
Bolt
up the level of
12 and
abstraction
for
make it
silent
easier.
payments.
So one of them,
We support
Jeremy
both of
mentioned
those
earlier, is
for
Sapio.
privacy
It's a
purposes,
really great system
and
for writing sticky
we
chains out of
because we
CPD
take
trees
privacy
that
pretty
has, like, a really
seriously,
nice Rust
and
DSL. There's a
also
tool called Bitscript.
we're on X if you want to follow
It's
us.
an interesting TypeScript DSL
And
that you write Bitcoin
there,
contracts in TypeScript.
we consider supporting Nostr.
There's
I
a
love
project
Nostr a
called
lot,
Bitcoin Wildlife
but
Conservatory.
the problem with Nostr is
Ray King might be
it's
in
all
the
secured
other
by
room,
public
but,
keys,
he's
and
been doing a
so
lot of really amazing
you
work
can
on
imagine
trying to build a
why
script verifier
we made that
in
decision.
script
So
using FCAT, and
that's
in order
about
to do
everything.
that, he's had
Thank
to
you.
abstract out a lot of the operations around like Merkle tree validation and lots of math. And recently he added sort of a
I have a couple friends in AI in the Netherlands that have been doing large language models for 15 years, and what they said about ChatGPT was not that it wasn't possible, but when would be somebody be able to harness that amount of hardware and that amount of speed, and it was 10 years earlier than they thought. It was shocked the whole AI community. I don't understand this at all. Why can't the same thing happen here with quantum?
There are so many unknown unknowns that I couldn't tell you that it couldn't happen earlier. And so what I would say is that we should take this existential threat to Bitcoin very seriously, and that if we want this to become the money that the world uses, for international trade, and we want to have some kind of governments involved or whatever, big financial institutions, this is something that they're going to want to be aware of and mitigating against, because the government already is. And so for Bitcoin to be taken seriously and for people to have trust in it for the foreseeable future, we're going to need a soft fork
As
like
you were describing the
P2QRH and
problem
Qubit.
with all these code fragments, I
Good
thought
question,
about
thank you.
Minidscript, which
Yeah,
you thought about too.
SecP256K1 has a Schnorr implementation, which is aggerable. Are any of those proposed? Yeah, are they aggregable or are they not?
So yeah, actually in the BIP I specified that we would include only one Schnorr signature, because there's the possibility that if quantum computers are broken, or like ECDLP is broken, then people can include arbitrary data in the attestation and receive that 16x discount, which is something that we would like to avoid. And so we only
have an
allow
idea,
for one
even as
Schnorr
an idea,
signature,
several
and
people have
that's
ideas that there's
because
things that we
also
could do with
because
CAT that
Schnorr
would be
signatures
useful to
and
try
public
out
keys can be
validate, that could
aggregated,
prove out
and so
demand or
that will
utility
be able to
for
support
CAT directly
multi-sig
or for other options.
applications.
Like I say that a lot, other people say it a lot. We won't actually see it, so we're trying to build that out. So one of the first things
Yeah, so
that we looked
my,
at
my
doing
question
was,
is
can we put
maybe
some
what you were actually
generalized
asking,
CAT
which is,
instruction, like
are
into
any of
Miniscript
those
and just use
quantum
Miniscript
schemes
itself?
able to
And one of
aggregate
the
multiple
problems
signatures
that we
into
ran
one?
into very quickly is
Good point. Yeah, so the one
power
reason,
and
there's
the
a couple
curse a
reasons
little
why
bit
we
with
still want
CAT is that
to
it's
support
very useful
SEC
to do lots
P256K1.
of different
One
checks
is so that we
depending on, like, which
can
fields you wanna
have
validate
at
and
least some of
which
this
things.
functionality.
And
It might
we
not
ended up,
necessarily be as
like,
secure
when we were
as
trying
if
to
it
figure
was
out how to fit that
implemented
into
in
Miniscript,
these algorithms,
it ended up
but
making
it's it's not quite clear
very,
if we
very
can
complicated to
have
express
similar
those things and
things
still
like
have it
ECDH
work with all of the
and
internal data types for Miniscript and for that program.
like key
So
tweaking and
the
all the
approach that
different
we're
things that
taking
we
now
get to do with SEC
is we're building
P256K1
something that's
and
sort
of course signature
I would say it's
aggregation,
more
right? So
user extensible than Miniscript.
it's not quite clear, and so
But
we're trying to take
ship
this
sort
as
of
like
standard
a
library
more
that covers all the common cases.
naive
So we
approach
have
to
sort
including
of
these
standard
signature algorithms
selectors and a
just
bunch
for
of standard
signing and key
gadgets for
generation.
kind of
And
doing
then we're using
assertions or
Schnorr,
checks
we're
against,
building on
like,
top
all
of
the
Schnorr
normal fields in a
for
transaction.
that
That's like what you wanna do
to
with
actually be
CAT.
functional.
And something
And
that
we also support
we
Schnorr
have some examples
because
around. They're not like
it
in the
is sort of
standard
like this
library, but they're in like an
hybrid
examples
cryptography
directory, is
approach
we take a
where
lot of
we
common
allow,
instructions for things that you would do
we're
in
basically,
Miniscript.
we
So
don't want to
have,
ever
like, a
reduce the
normal,
security assumptions of Bitcoin.
checksig operation.
We want to
We
just
have,
augment
like,
them
like
and
an HDLC
not,
type
not
thing,
replace
like a bunch
them,
of things that people do
which
with
might
Miniscript.
possibly
And we've, like,
reduce the
modeled those out in our
security
system to see, like,
from
how is this composed and
from
I don't think we have any
a
concrete plans
vulnerability
right now for,
standpoint
like,
if there is a
direct
vulnerability
interop
found
with
in
Miniscript, but
any of these
maybe-
other signature
maybe what
algorithms
would
that
be
are used.
helpful is like if there's common things that people are that we're using our tooling for, or other people are. Maybe
Yeah,
those would
two
be
small questions.
interesting,
If I understand this
to,
correctly,
confirm
basically all the Satoshi coins
Yeah, I was
at
more
some
thinking about
point
having test coverage
will get
for your
hacked
way of
either
doing it,
way
because
with
I
quantum
get that
computing.
this is a different tool for different purpose,
So
but
there's
if you want a
massive
sanity
incentive
check your own
basically
tooling,
behind
you
this now,
take the exact
right?
things in Miniscript and run the
Is there
exact same
anything you
puzzles
can
to
do
get
about
them, make
that?
sure you didn't screw
Like
something
you
up?
probably have thought about it more. I would assume no, but maybe you have. And then second is the SQI sign is like a very recent proposal, if I understand.
The conclusion that
like
some of
aren't
these
there like
proposals
more
are easier
older,
to
more
make tooling
proven
for than others was probably the most
algorithms
interesting thing to me. What's your
more
relative
available or
ranking
not?
of proposals
Yeah, well,
by ease
to
of
answer your
making
last
tooling
question
for them?
first, Sphinx or SLHDSA has been
that's a great question. Like, I should have
in the
anticipated that
works
question and
since
come up with, like, some
2015 or
partial
so,
ordering of
or maybe even earlier,
I don't have
2010. I think it
would
was
say
approved in
something
2015
that
or
I've
something
noticed
like
is that
that.
the shape of the tooling that you make for,
But
like,
there's also
CAT
Winterschnitt
versus
signatures
ends up
and
being
Lampert
very different
signatures,
tooling,
which are also much older.
in my experience.
Lampert signatures date
So,
back to
Jeremy
1977.
mentioned earlier
And
that
so
with CTV,
the problem with
what you're
Lampert
really doing
signatures, and
is
we
you're
actually go
building
into this
a
in the bit,
tree of what are
and we
effectively
compare
pre-signed transactions, and then
just about every
interactivity out of that,
quantum,
and you
post-quantum cryptography
walk
algorithm we
backwards
could
up
find.
the tree, and then you do a
And
bunch of, like, hash
so
grids.
we
a lot
found
of
that,
the tooling is kind of about, like,
Lampert
how do we
signatures are at
model
least
all these
64
future
kilobytes in
transactions
size.
and, like, the fan
And
out
then,
in a
there's
really, like,
also
ergonomic
public
way.
key. And so
Whereas the tooling that
they're
we've
not
found to be
as
most useful for
practical
CAT
as these more
is
modern
abstracting
implementations,
out
though they
how
might
you
be
do,
more
like,
secure
validation or
necessarily. It
composition
depends.
of
It
individual
really
things
does depend.
inside of one
Yeah, more time
transaction.
over.
So if you saw Jeremy's talk
yeah.
earlier, he
And the
kind of
first
talked
question?
about programming
Of
transactions
Satoshi's
for
coins?
programming
Yeah,
scripts.
Satoshi's
Yeah,
coins.
Found that for
They're gonna
CAT,
get hacked
it's
either way.
easier to build
Yeah,
tooling
so
that's programming a script, and for
if we were
CTV,
to
it's easier
prevent
build tooling that's programming
people from spending their
transactions.
coins,
I don't have, like,
because
a
like we've
strong
already
judgment about which one's
seen,
better, it's just an observation.
early coins move, potentially in response to this potential threat that people are talking about. If we were to prevent them from moving the coins, this would essentially, this could be a hard fork scenario, and that's something that we would like to avoid, just any controversy in. We want to just be very focused on what we do in Bitcoin, and something more ambitious can follow on later if it becomes, a larger concern. But we just want to, introducing a new address type and also introducing an attestation discount would be so difficult already. I don't want to complicate it more with even more ambitious and broad-ranging solutions to this problem.
I would love to keep going with questions, but we got to keep on a time schedule. Hunter, thank you so much. This is fascinating. people want to keep asking you questions, I assume they can find you afterwards. Okay, we've got Sean Ryan with OpVault, and over next door we have Paul Stort with CUSF.
You're welcome.
He really wants to talk about this, so I recommend go checking that out. Sean Ryan,
30 minutes, so
here. Let me know if you have
15 minutes of this kind of background lead up to the problem and about me and the context and the things that I think are important. And then 5 minutes on this thing, and then I do think the Q&A is really where the magic happens. So I think that the Q&A is.
Cool.
I'm going to say some pretty audacious things.
Hold this or talk to there.
It's only fair that people
choose
ask questions about them. But I do have a kind of a long.
All right,
intro
can you hear me?
slide.
All right,
So
I think this is
spoke at
good.
all three
I'll just talk through here.
of the first scaling conferences. I was on the program committee for the fourth. This conference.
I think this is good.
Supposed to be continuing in
I
that
don't
vein.
need that much.
But what happened
mic, I think.
after the first three, or really even the first two, is that the scaling conferences quickly became
All right,
pretentious.
so
junk.
today I want to talk about vaults for custodians. I'm Sean. I'm a product manager at Anchorage Digital. Anchorage is a Bitcoin custodian and a federally chartered bank. Although this is titled for institutions, I think it's important to point out at the beginning that anything, it can also be done by individuals. I think one of the powerful pieces of upgrades to Bitcoin is that it could shrink the size of institutions and kind of change the view that everything we're doing has to just be for self-custody. Self-custody is incredibly important, but it's not the only thing that people are going to use Bitcoin for as adoption grows. So in this presentation, I'm going to start off by going through BIP 345, which is OpVault. There are many ways to make a vault, but that is just one of the most narrowly defined opcodes, which is why I wanted to look at it. And then I'm going to look at some of the use cases.
A little bit of slow developer action that has translated to.
All right. So what is reactive security? This is not an official definition, but in general, it's the ability to recover from a private key compromise. Right now, as everyone in this room is probably well aware, if you lose your private keys in Bitcoin, your money's gone, and it's game over for you. I think this is a really big hurdle to Bitcoin adoption. This is, in my mind, almost as important as scaling transaction throughput, is scaling the security that individuals and companies can custody Bitcoin with. Realistically, unless it's easier to hold private keys securely, we're not going to see a billion people holding private keys.
Basically anticipated not only
And then vaults are a covenant implementation. They're kind of a use case that uses reactive security, and this helps you recover from private key loss. So if it's stolen, a vault owner will notice a trigger transaction, and then they can initiate a sweep to a separate wallet that they control. So I think having this extra layer of defense in custody is a really spectacular use case for covenants. And since it's so tightly defined in OpVault, I'm going to go through that one. But it's important to realize that there are, like I said earlier, many ways to make vaults. Rindale over in the other room has a perfect vault. You can use OpCat. I'm sure there's many other ways you can make vaults. So this is not the only way to do it.
The left circle is.
All right. Real quick. So OpVault was a proposal by James O'Byrne. It adds two new opcodes, OpVault and OpVault Recover.
The next one over is the fees in 2023.
In the BIP, it is used in conjunction with CTV, which Jeremy just presented on earlier. The TapScript opcodes, OpSuccess 187 and 188 are constrained with the new rules to implement OpVault and OpVault Recover. Just as a quick note, anytime a new opcode is forked in, it uses a set of reserved opcodes that are used for this. This is what makes it backwards compatible. And right here we have a graph of a basic transaction flow. So
later in the
over
talk,
on
so you'll be
the
able to
left
look it up if
side,
you're interested.
we
But
have a user who spends a
basically,
UTXO into
I
a
came up-
vault.
You know, I looked at like the population of the world.
And
that
then
is
from
over
there,
14 years
there
old
are
and
two
all sort of
options
stuff. So
are an
it's basically
unvault
$6.4
transaction,
trillion
which is
in
that trigger,
2024.
or they
Back,
can just sweep it into
trended back to
a separate wallet that they
2022,
own,
and then
and
the
that is
10
only
cents
one
per
address
transaction,
that is
because
defined
that's
at the
very
beginning.
low, and it's significantly lower than
And then
basically
after the
everything else
unvault
that
transaction,
exists. And it's
after a
so
time
low, but
delay,
you see, once you get to 10
then
cents,
the
someone
withdrawal
only
can be
undercut you by around
finalized.
9
So
cents per
it's kind of a
transaction. And I
phased
thought that's
approach,
probably not enough
and that's
to
what
get
adds
people to
the
switch
extra
from
layer
it.
of security there.
So that's kind of, I just eyeballed it as the equilibrium fee, but people are free to use whatever
Alright,
numbers. But the point is, it's a huge amount.
All right, this
And
is
the other thing is it doubles
a bit
the
of an
value.
involved
It
diagram
grows at
for
6.2%
for
a
op
year.
vault,
It
but
probably goes faster
as you
than
can see
that,
at the
that's our
top,
lowest estimate.
you have the initial vault construction. The two spend paths that I mentioned earlier,
it's something like 3 per day
the
per
trigger
person
and then the recovery
it's
path.
per year, right.
Those are two
So this doubles every
tap
11,
leaves.
12,
So that's where the actual that's where the conditions live. You see at the top, the
So
green
why did I
one
bring this
is
up?
the vault path,
Well, okay,
and
the first
the
question
blue one
is a very
is the
important one,
recovery
which is
path.
if Bitcoin took over the world, who would
It's
get
also
this
important to
giant
point
pile
out
of
that
money?
there's still
the
the
current
internal
intellectual
pub key.
climate
So
is
just with
pushing
Taproot,
these
you have
non-mined
both a key
L2s,
path
which would
spend
include the
and a script path spend. Everything in
rollups,
Opvault is
liquid.
happening in the script
These
path
are
spend.
not mined.
But if you want
L2s,
to
and by
be
that I
sure
mean the
that it's
transaction
constrained
fees
only
on
to
the
the script
L2,
path
they do not
spend,
go to the
you can
L1,
choose
Bitcoin.
a nothing up
Instead,
my
they go to
sleeve
someone else, they go
point,
to
which
the-
is basically an
the Lightning node that
unspendable
routed
key path.
payment, or
So
they
you
go to the
can
LSP,
choose
or they go to the
a
ARC
point
SP,
on Bitcoin's
go to
elliptic
the
curve
sequencer
that
or
has an
sequencer.
unknown discrete log,
So the money goes to
which
someone
means
else.
no private key that
And
someone can
of
spend
course,
with.
that's kind of rude to the
So
miners, but
that would
that's
be
not
one
really
way
why
to
I bring
constrain
up.
it,
It's
but you
really
can
much
also
worse than that.
use that to
actually
put like
very,
a very
very
deep
interesting
cold
what will probably
backup
happen.
key
And,
in there.
my guess,
But
this is a complete
for the rest
guess
of
on
this,
this,
we're just going to talk
I
about
don't see how it
the
can be
script
any other
path
way
part of this.
other than to produce this horrendously
Down on the
unstable
left
situation
is the trigger
that will end
transaction.
in
So you're taking
conflict
a
between
vaulted
the L1
UTXO,
and L2,
you're activating the trigger,
overall,
and
and
then
a huge
you
incentive for
have
miner
the intermediate
centralization,
stage. So
and then eventually vertical integration
after
between
this,
L2s
you would
and
be able
L1s
to spend,
miners,
but
and then
the
this
key
vertical
mechanism
integration will
with
utterly
Opvault
obliterate the
is
entire
that
L2,
you pre-specify
security
the
model in
format
first place.
that
L2 will end up fully
that this
custodial,
intermediate
possibly
UTXO has to
even
take.
minor custodial,
And then so if
and
you
then
see
the value
here,
will all become MEV, in
it
fact,
still
so
has
you know,
the recovery path.
later.
Um, and then it does use CTV in this
reason that- let
diagram
me explain a little
to
bit more
enforce
about this, which is
that
to say, so
the
the miners get
that the
this
tra-
tiny
the
circle,
trans
and then there's this huge circle
the
above going to,
UTXO
like, the arcs
is of the correct format.
The reason why this is actually
Over to the
important
right, you have the
is that
recovery
the
path,
miners have an
which is
extreme
available
ability to
both in
affect
the
the
beginning and in the intermediate
Every
stage.
L2 is vulnerable to 51%
It does have the BIP was designed to be compatible with V3 transactions and to use ephemeral anchors for fee bumping. Since if you're using a vault for deep cold storage, you probably can't pre-specify the fee rate. So we don't have to spend too much time on that, but it was designed to work with that. And then just lastly at the bottom, you have the withdrawal, and that's when you withdraw the time locked output that follows the format specified in the original vault.
You pull this on L1 and you can slash their bond or whatever.
All right, and then so we have
the different L2s are very
creating
different
a
from each
vault.
other, of course, but no
This
matter what
is
the L2 is,
this is
the miners can block the entrance and the exit.
witness the script pub key that you spend into.
There's a little bit of animosity.
As you can see,
go a long way.
the paths again,
So
the
basically, if we
leaves
return to this
are both the
example where you
recovery
have, like,
path
something like a
with the
foundry
Opvault
LSP,
recover.
or
So I
AMP4
highlighted that
LSP, a
since
foundry
that's
lightning
one of
on
the
one hand
opcodes that's getting that
versus
would
the
be
lightning
added with
nodes
this.
that are
And
not
then
backed by
then you have the
giant
trigger
amounts of
path.
hash rate.
And
Then
so
it
this
would
is
be
just kind
completely
of
understandable for the
a more
actual
in-depth
end
look
user to get nervous about
at how the
using
trigger path
non-mined
works.
LSP. Because they would not be secure.
The leaf update
And
script
HTLCs
body,
really do nothing.
that can be
And eventually it
you can
online,
basically
run
put
an
anything you
online or
want in
associated
there,
LSPs would go out of business,
because
and everyone would use a minor
it's up to you
LSP.
to determine
All the
what
HTLC stuff would
what
be
format
superfluous,
will be
and the Lightning security
applied
model wouldn't even
to
apply in this case
to
anymore.
that next UTXO.
And the interesting
So
thing is that
it's
all of this,
it's got
the whole
lots of
L2 value
options.
is a giant sphere or a giant
You can pretty much put whatever you want.
that would all become MEV, since it would now become
All
mandatory
right,
to
and then
run.
so this
become
is this is what it looks like to trigger a withdrawal. At the top, you have the witness stack. So this is what would unlock the original output, the outvault output, and then below that is the output script for that intermediate transaction. So when you're triggering it, I think the most important thing to keep in mind, which is why I highlighted, is that spend delay. So if you see the recovery path still exists, but then in this new output, the spend delay is really what gives you that extra security. You can choose it to be however long you want, but having that spend delay is really important because that's what gives you time to react.
I think this means that they can never really be big. They can never really be a big success because as soon as they're a big success,
also you can also include a revault. So when you're spending from a vault, you obviously don't have to spend all of it. You have the option to revault a portion of it into the same construct that you had earlier.
Well, why don't we start our own, mining LSP, Foundry LSP, and then they get into a fight, and it is a battle where one of the sides doesn't have any.
Now I kind of wanted to look at why this is important and how this applies to the real world. I think Bitcoin is going to continue monetizing, and it's going to be used by companies as well as individuals.
But basically, it's a very small.
A lot of the covenants and soft fork proposal debate has been really focused on what does a peer-to-peer transaction between two people look like. While that is clearly important, there are already companies that are using it. It's going to be adopted by nation states. It's going to be adopted by the largest companies in the world. And they enter into complex agreements that individuals don't enter into with each other. And so I really want to drive home the point that the terms of these agreements right now are mainly held in just paper contracts. So custodians will have lots of contracts. And if we see really big Bitcoin adoption coming up soon, they'll probably also be using really complicated contracts. You can probably imagine companies like BlackRock will be doing this. So I have here that you can have it either like financial agreements by people who are adopting Bitcoin will either be strictly defined in legal contracts because they're using sort of a basic custody setup, or the terms will be trustlessly enforced by Bitcoin in addition to having legal contracts. So if there's one point I think if there's one takeaway from this, I think it's that it's really important to have as much of agreements as possible to be enforced on-chain on Bitcoin. That has the best trust assumptions. It's why everyone loves Bitcoin in the first place. And I think it's important to really realize that right now, a lot of the economic adoption and the economic actors that are using Bitcoin are basically not doing this. All the Bitcoin that is in ETFs and structures like that, the ultimate agreement as to who owns that is right now something that would be settled in courts basically, and not like settled on chain.
I mean, kind of difficult to
obviously the owners of the private keys still control the funds, but I think an important goal for a scaling discussion with covenants, with vaults, with any of this stuff is to just really get as much as possible like granularly defined on chain. And then so features like velocity control, spending policies, and layered security, I think dramatically improves Bitcoin's utility as money. I think a lot of Bitcoiners kind of have this notion that the price will magically be in the millions, and then one day they'll just rule the world. I don't think that happens without really improving the utility as base money. So by base money, that means it's going to be the backbone of the global financial system. And
list
with the way
suggestion of the
that
idea.
custody and script works
So
right
when it
now,
was coded, and
I
then
just
when it
don't
was
think
actually
that it's
activated, and
equipped
so
enough to do that.
You can see SegWit was 20 months and Taproot is 46 months.
All right,
And
so
think
I want
if
to
you
sort of do
been,
a quick
paying
question in the middle
attention
here.
today you see that there's all these
What does
ideas,
anyone
but
here
everyone
think
has
is a
this
use
for
case for
whatever-
Vault,
every single
both
idea is always put forward,
both
that's
personally
a
or
idea.
for a
And
company?
so
Does
there is
anyone have any?
no actual consensus on anything, and so that
Yeah,
is why
recovery.
there's this
That's
logjam.
that's I think a great one.
So this is the first,
I think it's a huge
roadblock. The
challenge when
second
people are
roadblock,
first
though, is
getting
you
into
really cannot
Bitcoin.
just switch away from Bitcoin
You
Core
know,
to something
you'll
else.
tell
It's too
anyone
drastic of
that
a
hey, you
change
should
for a
self
variety of
custody.
reasons.
You need to hold private keys, but oh by the way, if you
like,
mess it up at all, your money's gone. So I think
like
that
to
recoverability
leave it for
is a
completely
great way
different client, it might
to sort of
disconnect you from the
onboard people.
network, and it might you
wrap
might wonder
Bitcoin,
like who's
but
going
without
to
a centralized custodian.
in the long
Yeah,
run.
yeah, that's another good one.
You can't
So
do that
wrap
type of
Bitcoin without a
thing. There's
centralized
no
custodian.
way to actually
Right
compete with
now,
Bitcoin Core with the second
because
client.
of the way script is,
One reason is they have these CVEs
it's
that
kind of
are only disclosed to them.
incentivizing
They're the only ones who know about
centralized
the security
custodians to be doing that service. So that's
They
another
sort of
good one.
must keep secret. And
Any
so
others?
this is just one reason among many why you
Social
cannot
signaling by large entities like ETFs.
write a competing client, basically. And so this
Yeah,
solution
that's another
here
good
is that
one.
you
So
keep
social
Bitcoin Core
signaling,
completely unchanged, and you just keep, it's
I
almost like a
think
dependency.
that's, yeah, that kind of
It's already
parallels
there,
a
doing its thing,
pretty
same
public
thing it did
example.
before.
With
And
ETFs,
then you release a second piece of
for example,
software
some
that
of the
manages the
issuers
soft
make
fork
their
only.
on-chain address known.
And that is called,
Everyone's going to look at
that
that,
would be the key
and
set
if you
activation.
have an
after
issuer
Bitcoin
that's
Core
using
scans
a
a block,
vault, and
passes the
all the
block to,
other
like, the
issuers
FCAT
are using
activator, for example.
legacy address format,
Scans the block
I think
again,
that's
and then
great
if there's any
signaling
opcat
and
rule
also just better
breaking over there,
security.
that's the only
So
thing it's
I would agree
scanning
with
for.
that.
Second thing. Then it tells Bitcoin Core to reject the block.
All right, so I think one thing that
Makes the
this.
soft
Oh,
fork,
did you have another?
it's much faster, safer.
Oh, sorry. I was
gonna say
understand.
collateral then.
This
Oh,
sense
really?
in particular, because
Nice,
it's a
you,
little bit more reversible. You don't have
yeah,
to, like,
so I guess
start
you
the mining operation. You
predicted
got the
that
second
one.
piece of software.
Yeah,
and if the
so I
second piece
think
of software is,
right
low
now,
quality, or if it crashes or
a
something,
lot of people will
there, the software
analogize Bitcoin to gold.
temporarily deactivates in that situation, but it
You know,
doesn't
it's
doesn't affect
base
any-
money,
doesn't have to
and
affect
I
anything
think
that is currently,
collateral management is a
running. I
great
mean, it's a
use
nuanced
for vaults.
question, if
If Bitcoin's going to become the global reserve currency, it's going to be used similarly to the
site.
global
This is just a
reserve
site that I
asset,
grabbed.
which is U.S. government bonds right now. Unfortunately, I think people tend to ignore this because they think, oh, government bonds, that's fiat nonsense, it doesn't matter. The reality is that nation states across the world, and really everyone, uses government debt as a reserve asset. And so I think it's useful for us to keep in mind how those markets work and realize the possibility that people might try to use Bitcoin in a similar way if it grows to that size.
So the software already exists.
So,
you
and I
can
pointed
fork
out that
this software and you
fiat
can
products
make a
have no
CDP
custody risk.
activator or whatever.
It's kind of funny to even say that. It's just a ledger that they control. But right now, there is significant custody risk for Bitcoin.
Really no
If
different
you
than how
lose
any
keys,
other
it's
software
gone.
could activate.
And
Another way
I think if
it's
something
very
is acting
It
as
has the same
collateral
effect
to the
as
global
a soft
financial
fork.
system,
I think
that
one
kind
interesting
of
thing
risk
about this
and
idea
worry
is that most people don't
is
understand what a
unacceptable,
soft fork
and
is or what it's
it
doing.
will frankly
And
hinder
as a
adoption.
result, this is
Yeah, so I think we need
like, the
stronger
best way to
on-chain
explain it is
security
what a soft fork
guarantees
actually is
if
and
we're
why
going
it's,
to replace government debt as pristine financial collateral.
But it has the same effect, but there's two different.
And then I
software,
put in this graphic right
demons,
here,
and there's,
I have the just the daily
it is
trading volume
inefficient in the
for
sense that the computer basically
from
has
like
to
the New York
do
Fed
twice as much
of
work as the
reverse
smaller
repo
blocks at some
operations. So that's
But it's
overnight
more
secured lending and
efficient in the
borrowing
sense of humans,
with government
because
bonds,
we don't have to get a
and
pull
it's in
request
the
through
hundreds of
Bitcoin Core
billions
because
every
they do
day.
not want to do any controversial
So
pull request
I think
ever,
the
and
main
as you
point
can
of
see,
this
it's very easy to
is just that
manufacture
the global reserve asset right now is used for a huge amount of secured lending and borrowing. And if Bitcoin is going to replace it as the reserve asset, we need better on-chain mechanisms to allow it to do those functions.
I think the idea is
Yeah, and then so I have another
miners run
question.
this to scale Bitcoin,
If you had to
miners
hold
run
$1
this
trillion
with
of Bitcoin,
QSIF
how would you
activator.
do it?
Bitcoin Core
Would you be
continues to do
comfortable
nothing,
doing
which
that right
they're very
now?
good at that, so.
So I
And
would love to hear if anyone
once
has
that 51% hash rate
has an
is
answer to
running
that.
it,
If
then
you
it's
had
activate. It will only
$1
activate
trillion
for as
of
long as they're
Bitcoin,
running it. And then, of course,
what would you
regular
do with
people
it?
can run the
Would you
activator on their
be
own.
comfortable with that?
to do that, to
What was that?
validate the rules. Probably would be the full
Zapo? I'm seeing
And the miners
some
activate these mined L2s, and they
shaking
collect money from
shaking
them, and
people's
then Bitcoin
heads.
has scalability, privacy, et
Anyone?
cetera. And I had to compare
Multi-sig?
this to the,
Yeah.
I think the alternative
Giant
plan
multi-sig?
is to take the same people
get
who
nervous
for
even
years
using
have been
multi-sig
overly
for
optimistic about the viability of life.
Yeah, that's totally fair. I
Wait
mean,
for them to finish ARC or whatever,
using
some other thing,
multi-sig
there's not even dev
is
tools,
obviously really powerful.
which is going to be way worse for the end user. It's more
but yeah,
complicated, more expensive.
it's arguable whether
And
that's
it may not
approachable
work at
for
all,
enough people.
and then such that even if it did
if
work,
you
the
if you
miners
imagine a
won't get any
world where
money,
individuals are holding their life savings and massive amounts of wealth personally, and at a scale where hundreds of millions of people are doing that, I think it's impractical to just tell them all to make their own multi-sig. So that's just a kind of another reason I put this out there. Something like vaults, something with reactive security that improves on-chain security, I think would allow that feature.
then that doesn't look great for us. So I think.
All right, and then here I
tons
just
of
have
extra slides, and I have even
a
more
quick graph
stuff,
of Bitcoin
but I would like- I think
in
the
terms of like the
questions are far more
size
important.
compared to other
if you don't
global
ask any
assets.
questions, I will do random slides.
I think this is something that it's important to keep in
Maybe just
mind
yell it out, I
because
think
the big pools, specifically bonds, money, and gold, are what Bitcoin seeks to replace as a global store of value. I think people oftentimes dismiss these kind of ideas and act as if Bitcoin has already won. It's certainly on an incredible trajectory and has lots of potential, but like the previous slide mentioned, if Bitcoin is going to claw into these markets and really become the backbone of a global financial system, people have to be aware of how these larger markets work and really try to be practical with how Bitcoin will sort of take over that market share. And that's going to be both companies doing it and individuals. I mentioned that nation states typically hold all of their money in U.S. government bonds. Most people hold, most non-Bitcoiners will hold most of their wealth just in the S&P 500, for example. So I think it's important to keep this in mind when you think about what it looks like for Bitcoin to take over as money.
Okay, let's think about it a little bit more like this. The new soft fork is just this is.
Okay, and then I think another really good use case for vaults are provable time locks. I have this graphic up here of the scary man with the wrench, because the $5 wrench attack is something that people talk about all the time. In self-custody, I think a tangible example would be, if someone breaks into your house and demands that you give them Bitcoin, you're likely going to go to a hardware wallet and then
This is a terrible idea
or
to have a
just an
separate piece
account,
of
and they'll
software,
compel you to
especially
give
if
it
it's
to you.
something like Python, because
This, by
if
the
you
way,
do
happens
succeed
more
in
frequently than people might
getting
think.
the soft fork activated,
Jameson
then
Lopp
that
has been
Python
keeping
code
an
with
active
whatever
track
subtle bugs it
of all these
has
incidences,
becomes consensus,
but
and
I
somebody
think
like Bitcoin
a
Core will
vault
have
setup
to then
where
re-implement it in C++
both the
and make
unvault
it
and the
permanent.
recovery
But
path that I
kinda
mentioned
what I would
before,
suggest here is if you
if
want
both
to
of
activate the
those
software
are
this way,
time locked,
just make a patch
then
of Bitcoin
you
Core,
could
and
provably
yes, your pull
not be
request
able
might
to
never
give
get
up
merged,
custody of
but you
funds.
can always just release
And so
your
even
own
if
Bitcoin Core
you
version that says, like,
followed
this is
an
identical
attacker's
to Bitcoin
instructions,
Core version
you basically would
1.29.0
have to
with only this new
have to
opcode
do a
added.
trigger
The reason why that will not
transaction
work is because
that
of
could
the
be delayed
rebasing.
for up to a week.
Yes,
And
rebasing an opcode
you
is
could
not
say,
hard.
well,
I
time locks are
disagree.
already in
I think you can do
Bitcoin. But I think it's kind of impractical.
I
Like
would say
right
that if you
now,
can do that,
most people aren't
I
going to
refuse
just
not to be
perpetually
doing
time lock their funds
The
to guard them.
rebasing is like an endless vampiric,
But if you have something like a vault
draw on
that
whoever
requires a
wants to
trigger
do
transaction
something new.
and then a
I see, we need to
predefined
get-
period of
see, this is
time,
the issue. The
I
issue
think
is the
that
existing thing
could
doesn't
dramatically
work.
reduce
So-
the
and the other
threat
thing is, I had this in extra
to
slides.
key
I know
holders
I'm,
at
like,
home. So
scamming people now with this.
that would be the
But, like, I
individual
read
sort of
this paper, which is a
self-custody
very cool paper I read on
scenario.
the train ride up here. But
But also, if you think about smaller companies, smaller groups, right now it's not really feasible for a company to have its treasury custodied by like a group of individuals with hardware wallets in their house. But I think if something like vaults gets adopted more, then that could really reduce the incentive for people to basically be $5 rent attacked. And no matter how much that's really happening today, I think it's a constant fear and a constant concern. And when people are thinking about whether or not they can custody Bitcoin themselves, it's something that is likely on people's minds. So if the incentive to perform that attack is lessened, then I think that would just be a huge benefit to all of Bitcoin.
There's the risk. This is the whole point of this idea, is it concentrates the risk.
And then the last example I wanted to bring up that people also might think is kind of a boring or irrelevant topic is insurance. Right now, the custody insurance market is very small relative to Bitcoin's market cap. There's a company, OSL Digital, that recently announced like a $1 billion insurance policy. Most people believe it to be the biggest. It's frankly pretty hard to find good data. I spent a while trying to find like the size of this market, and basically found that it's so small that it's difficult to know. I think this is important because going back to that sort of graph of relative sizes, there are certain types of companies, types of groups that aren't even going to touch something if it's impossible to insure. But that the National Association of Insurance Commissioners currently considers Bitcoin uninsurable. And I put a container ship there because
a lot of
really
questions, but I'm sorry, we're gonna have
a
to
lot
move on
of
to the next
things that
one,
are
so
large
Marshall,
scale
sorry.
and important for
Trey,
economies
sorry,
to do,
anyone else who has
like
any
buildings,
questions, but if you do,
like shipping
grill
things on
Paul
containers.
out in the
Those
hallway
are
over
those
there,
are all
or in the conference room
involved in
on
insurance
floor
and
14.
reinsurance
Also, there's
markets.
coffee out there now for anyone who needs a little bit of a
I
pickup.
think that
but with
risk
that,
sharing
thank you, Paul.
is a really
Appreciate your
important
thoughts,
part
and
of capital formation and an economy.
And
I
for our
think
next talk, we have
Bitcoiners
Tad
can't really
Strija
write that
talking about
off.
scaling
If Bitcoin is going to
L1
be global money and truly adopted, then I think similar
on the workshop
markets
track,
will
we
have to
have
form.
an op vault,
And I think
demo,
vaults kind
with Sean
of
Ryan. So if
would
that's of
really
interest, head over there.
help that to become a possibility, and make custody like kind of an insurable activity. And it might sound goofy, but I think that is important and would grow adoption. And that's it. And so any questions? Yeah.
Paul to the principal's office.
I guess the question is what makes the current state of multi-sigs for vaults like not insurable.
The reason we're having this conference.
I think
is to
right
talk
now
about
it's just
what Paul was
because
bringing up. So
it's kind of
feel free to grab
too
coffee.
nascent, like
this
in terms
conversation
of
also might be a little
it
interesting.
requires a really good
So
setup.
I'd say
I think
stick around,
there's
but
not many
if you
companies
are going
that
to have
are,
a conversation.
I think there's
step
one actually, I
outside
guess,
the
that's
glass,
doing
please.
that's
So we can all
doing
hear inside here.
multi-party like shared custody with multi-sig,
quickly.
but I think the short answer is just that it's hard to do and people aren't doing it.
Okay, so I'm going to talk about scaling L1.
Yeah, and I think
it was great to sit through
closing
some of
thought I
the other
wanted to
talks
say
and,
was
and,
that
like there's a lot of overlap.
something
which
like vaults
is
or
good
things that
because it's
improve
like,
people's
we
ability
sort of
to
agree on things,
custody
but also I'll try to
will
run through the parts
simultaneously
that if
improve
you've been in
companies'
this room since
ability
this
and
morning, you're like, yeah,
individuals'
someone
ability
else already
to do
talked about that for
custody.
5 minutes.
And I
So
think
Tad
also
Strija,
sort
work
of
on Lightning Network, discrete
shrink
contract,
the
UTXO, working
shrink
on
the
IT,
size of companies.
Yeah,
You could
out
have
there.
Two or three people have the same security as like a nation state. And
sort of like a
I
GPGT,
think
but
as
people might
proof
actually
of
use
this, there's probably people
so the
at this
first question,
conference
and this is
whose
something a lot of
self-custody
other people
setup
have been
is
saying,
more
like, okay,
secure
what's Bitcoin
than
for?
like a TradFi bank.
I think Paul
I think
just
that's
said, like, oh, this
incredible,
doesn't work.
and that's
I'm like,
something
well,
that we need to
some
further.
people, it doesn't work for you. Like, we don't
script
really have
improvements.
consensus on what this whole thing is for, right? Who even
Rock on.
decides what
Thanks, Sean.
Bitcoin's for? Like, Satoshi? And Satoshi clearly was unclear, right? It's like, yeah, we're talking about vending machines and like micropayments. Like, oh yeah, you can totally do all these things. But then he's also
Tad
talking
just
about,
kicked
banks
off
must
next
be
door,
trusted.
scaling L1.
And it's in
We
the
have
same
Waking.
line, right? It's
Here,
like this sort of,
I think we have the
empathetic-
two
well,
greatest
this
minds
is-
back to
this
back,
is fidelity.
opposite rooms.
But like this sort of like hodler, we're gonna take over the world. And then
Waking
right
titled
after, it's
Starks
like,
and Other
massive overhead makes
Shenanigans.
Micropayments impossible. So it's like, wait, so are you trying
yeah.
to
And I got
like
this,
replace the dollar in gold, or are you trying to make micropayments, or I guess both? So it's not really clear, right? So the use case number one.
It looks like
is
we'll have
go up
an
and people,
intimate crowd
said this.
for this one.
And
but it is recorded. There's a couple hundred people
like
watching
that.
online.
We'll talk about this. This is a big
The,
thing.
well, clearly
Use
the
case
other
number two,
call,
I guess,
right?
is whatever this is. I don't really know. It would have been really cool if we could get AC to this thing or something. I don't know.
Let me
what people
just
do with
like
this
get
large
the
vesting.
slides
It feels like some kind of gamified investing
Okay, I
thing.
think it works.
But
Should we
this
wait
is
for a
not
few minutes
necessarily what
or
I
like
expected.
the other
getting
one's
into
already
Bitcoin,
started,
10
right?
plus years ago. But maybe we shouldn't be surprised.
Yeah, they just started.
Right?
Okay.
Like this sort of the
Okay,
number go up
then let me
actually
just
makes a
kick
lot
off.
of
Like,
sense,
anyway, you
right?
have
There's
the recording.
tons
so.
of people that have very restricted
You
access
have the
to good
recording,
investments
right?
and ways
So
to reserve wealth.
Of this?
But
yeah.
generally, they
so
have
it
ways
will-
to buy
it-
things at
yeah.
the store.
Okay.
Right? So if
This
you're
will
in,
be
I don't
recorded.
know,
Be
Venezuela,
available
like,
for streaming out.
well, probably
Okay,
you,
no
you can
problem.
like buy.
Yeah,
things
we'll
at the
just
store.
finish
It's not
that,
the,
yeah.
it's not the transaction.
probably go
problem.
grab a
It's
couple
not that like,
people
oh,
back
my
here.
transaction fees are very high for dealing with this cash.
Well, it's always
It's
the case
this
that
cash,
like because in the other conference
decays
there are
very
also not a
quickly.
lot of
It's
people
worth
working on
much
OPCAT
less
related
than it
stuff.
is now.
So
That's
I
the
will just
problem
keep
that
out
we
this
have.
live
I don't really
presentation,
know of any
but
country where
you
people
are
like,
aware that the
yeah,
other room
there's no
also have a
inflation.
presentation
We
that
have
is
like
going on
1%
right now.
inflation.
So
That's fine.
yeah.
It's just when you go to the store, they
So
tack
let
on
me
this
start with this
50%
presentation,
fee
and this
using cash or
presentation is
credit cards
basically
or any
going to
bank
talk
transfers.
about like
Right, like, I've
stock
never heard
and
of
that
that, right?
like
where
how
the
they
bank
do with like
transfers are
OPCAT.
like a huge part.
So
Somewhat
I
reminiscent,
will
that
talk
was sort
about
of
four
an
things.
argument
First of all is
a
to
long
give
time
some
ago, but not
background
really.
on stock, and then I will talk about why OPCAT would be like important for like stock to work.
Sure.
And
There are
like
case
why
studies,
it would be
but it
very
does- and
difficult
so,
if
like,
you
that
don't
was sort
have
of the
like
thinking.
OPCAT. And the
But
last
it's like,
point
it
will be
makes
about
sense
that
that
like
this is why people
how do we
right?
have implement this like stock
Also,
to
Gresham's
verifier.
law, which is the law that like good money drive or bad money drives
Okay,
like good,
so
or good
we
money
will
drives
start
like
with
bad.
like
Anyways,
the
I
background
have
of
very
like
much
stock.
experienced this. So I was at
So
SatsConf
I
last
think
year.
the first point
It was
that I
really
want to
fun.
make is because
And,
that like
they
I think
didn't have
ZK
green
still
coffee
have a
water.
new things like for the like Bitcoin
hot there.
people because like most
and
of
they
the
were like, you
like
can buy
basically
bottles of
Bitcoin
water
have
with-
on ZK, but that's kind of like only early 2 years. And later on, like Bitcoin have never really get touch of the ZK. Well, at the same time, ZK actually have developed it like quite a lot. So I think one of the reasons why people have been skeptical about ZK rollup or ZK layer 2 is because that people think ZK is actually a relatively new technology that is probably not like stable enough to be used. But ZK is actually something that is like pretty well studied, like and have been used like for Ethereum layer 2 that actually allow the access on like Ethereum ecosystem that is now secured by ZK. Or in other words, is that if ZK is broken, those like assets will be stolen, but they have been running safely for quite a few years. And privacy payment have also been using ZK. And this actually have been battle tested for at least 5+ years. If we count privacy payment, like that would be actually have 8+ years. This is even older than like SatWait. Okay, and one thing that people might be wondering is that, okay, even if ZK have a long history, but a lot of the ZK algorithm that you are using are kind of recent. But like, and people will wonder whether or not this new algorithm is kind of like stable enough, have they gone through enough testing. Here, I want to use this slide to kind of show you that like, all the new algorithms are actually kind of belong to like our knowledge about ZK system in general a few years ago. This is a slide from 5 years ago. And this is basically a slide at that time that kind of classified different kinds of the ZK proof system and put them into like table and together. And here, what interesting thing is that like, you can basically do all the, wait, is this one okay? Okay, but basically is that like all the ZK algorithms are basically belong to 3 different families. You can basically classify them. And like, and even 5 years later, this like classification still work. There's no algorithm that fall beyond like this table. And all this table, and this table basically are talking that like you can actually, all the ZK algorithms are being built up by small components. And if you apply a compiler onto that, you compile it into like, let's say a ZK proof system. And here I have basically 3 compilers. compiler A, like from compiler A, we actually know one algorithm that is like quite popular, Grok 16, and from the name you can guess that is from 2016. Compiler V actually give you like Flunk that is like currently BBM is testing over. BBM also is working on Grok 16. Compiler C is the one where like all the stack and like stack related like system are based on. And still today, these three compilers are still the way that people get ZK system like here. Okay, so now I will kind of like just give a very quick like introduction about ZK. The idea is that like so how ZK works is like this: is that like you have like statement that you want to prove, you convert them into like a number of the like polynomial, and you want to check that this polynomial will satisfy some relationship. And I can show you a very simple example. Let's say that you have three polynomial ABC, and you just want to do a very simple test that like A times B equal to C. What like will be happening in Stack is that like Stack will commit this polynomial, and by commitment, here is a very specific way, is that you just evaluate this polynomial on a bunch of the points, and then you kind of just like put that value evaluation onto like a Merkle tree, and you kind of commit all of that. And like here, I use a number omega. Omega is basically what we call group generator. And it will just be a number. And you are basically evaluating the polynomial over the powers of these numbers. And here I talk about like the degree. 2L times D, 2 to the L times D. D is like the degree of the polynomial ABC that you are committing to. L is a parameter that is mostly for security. But basically is that if you are committing a polynomial of degree D, you don't just commit that. The commit actually an extension over that. So you are committing more points than what is actually needed to recover the like, polynomial. And so the commitment of a polynomial eventually will just be a Merkle tree, will actually be the root of the Merkle tree. And like on the leaves of this Merkle tree is basically just evaluation of A and ABC over like those points. One thing that I want to point out is that like you don't actually need three different trees to commit A, B, and C. You can commit them on the same one. Like you have one tree and you put and each of the leaf will be evaluation of A, B, and C put together. Okay. And back to the Stack is that like, so what Stack do is that like you now have those polynomial. What I want to show is to check whether A times B equal to C. And there's a mathematical result actually tell you that if you want to test that, you can actually test that on a random point. Like basically that, let me just find a random value. Okay, let me check whether on that random value, ABC will equal to that. And if it is, with a very high possibility, this will be true. And all you need to do is, let me kind of point out here, is that you just need to make sure that like this random number that you are picking is from a sufficiently large space. So it's kind of really random. And then what is the rest of the verifier job is it basically is to test that like, that's a specific polynomial to be low degree. And why is this step necessary? Here is the problem, is that like if you look at the first paragraph here, the evaluation on ABC is not from the Merkle tree, but is provided by the prover. Like prover just tell the verifier that here is the value of ABC on that specific point. Verifier need to verify that, need to make sure that that is actually the evaluation on those points. And what the like verifier do is basically to show that. So this is like actually there should be a randomizer there. But the idea of this like polynomial is to show that like if A on zeta actually evaluating to the value that like the prover provide, then this will be a low degree polynomial, otherwise it wouldn't. And you can do the same thing for B and C. I should actually adding a randomizer before the term of B and the term before C. But like you kind of get the high level idea is that if this is a polynomial, it means that like the value that prover provide actually match. And this will be done by using like the leaves of the Merkle tree. And remember the Merkle tree that we present here, but basically that in Stack, what you do is that you just randomly select a bunch of the leaves and check and run what we call low degree test protocol to check whether like the polynomial here, T, actually is a low degree function. Okay. And that is kind of the idea of like the start. And like, while I only give very high level idea because I want to use that to just to tell you what would be the component of a start verify. You will have two parts of that. First of all, you will do a bunch of the operation over the finite field. Second thing is that you will be opening the Merkle tree on a bunch of the leaves. And this is actually all the overhead of a start verifier. And this actually is a good size that like when an algorithm is simple, it kind of means that he have been kind of studied for a while. It's kind of quite, I would not say elegant, but basically that like it actually follow a very specific way to construct the protocol, and that like it wouldn't be kind of too complicated. Okay, and the second point I want to mention, and probably this is why you do need FCAT to make start proof verification efficient, is that like there are two reasons of that. The first one have to do with the Merkle tree. For like start protocol, you have to use Merkle tree. There's no alternative for that. And without FCAT, like Bitcoin, although Bitcoin have like hash opcode, they are not very useful. Like you cannot just use the hash opcode to do the hashing. You have to write your own SHA-256 implementation in Bitcoin opcode, and that can be very like inefficient. But with FCAT, you can do that very easily. And here I actually have the code. Well, it was written in a little bit pseudocode way, but this is the actual Rust code that is being used to generate the script to do the like Merkle tree. But it's actually very simple. What happened here is that like the whole picking is a pseudo opcode. It basically pulls an element from the stack. And all you need to do for Merkle tree is that, okay, is this one the left element or the right element? If it's left, I will switch the order. That's what this line is doing, doing a conditional swap of left and right. And after swapping, I do an FCAT, and then I run the hash opcode, which here the hash will be run by like it will be converted into SHA-256. This will allow you to kind of like do the compression as required in Merkle tree. And like you basically do this for every layer of the tree, and you end up just comparing whether it matches the like Merkle root hash that you are provided. This is a very simple code, and you don't need to touch the hash function. Like don't need to really emulate the hash function. This is reason one. Another reason why like FCAT can be very useful is that FCAT gives you recursive covenant, and that can allow you to split like execution into many smaller transactions. And this will be very useful because if you have a transaction that is large, although it can still be put into one block, meaning that like the script will be smaller than 4 megabytes, there's still some problem. First of all, you cannot easily submit this through like the P2P network. You probably need to work with some mining pool that actually accept non-standard transaction. If you do with Livestream, the only problem is that there will be a double fee. Like they basically double the fee that will be charged for that. Another problem is probably more like from the network perspective is that if you always have big chunk of the transaction that might take almost the entire block, they might actually like, they will affect the user experience. And I want to kind of explain that a little bit more. Because people may ask me that, okay, what would be the differences? Because if I have smaller chunk of the transaction, and I put them together, would that really affect the user experience that differently? That actually have something to do with like tuning. Why? So I actually can kind of use a simple example. Let's say I'm in Disneyland. There is a standby line and there is like a lightning line. Lightning line is where people pay to kind of go quicker. There are different strategies to like decide the gas because usually the standby line and the lightning line will both have gas. Some of the gas pay more, some of the gas pay less. There will be a strategy on like by the cast member to decide how many standby gas will go to the next round of the like show, how many from the lightning will go into that. And there are clearly different strategies. One way is that, okay, if there are lightning gas, I always let them in first. This might cause a problem is that if there are so many lightning gas, standby gas will not move forward at all, right? This is exactly the problem for a large block, is that if a miner say there's a large block, I want to accommodate that, all the transactions that are pending will have to go to the next block. But if you allow some transactions to go together, the average wait time will go down. And why? Why is that the case? Because you need to know that like for Bitcoin transactions, they come and go, right? All the transactions probably coming at a specific time. And what really affects the user experience is that when I send out the transaction, how long it takes to kind of get it merged. And it has to do with like the strategy how you have like handle this. And if you you can split the transaction into smaller chunk, the wait time for like non-big transaction will actually go down. Okay, and OpCat can have recursive covenant, and so it can actually, so if you have big transaction, you can also always slide it into smaller chunks so that all the block can still carry out something. This is also useful because unless you really want your big transaction to be settled in one block, otherwise this will also provide more flexibility. Okay. And the good thing here is that like each of the transaction after splitting is all small enough so that you don't need to use like slipstring. All the miner will accept that. This might be actually better than using slipstring. For slipstring to work, you need to wait for Marathon to mine the block. But for this to work, you probably just need to wait for the next one. And that, like as I mentioned, it doesn't affect other transactions like that much. Okay. First of all, I probably want to pause here. Like any questions so far? Okay, let me kind of move forward. So the next thing is that OpCat kind of give you a very powerful like primitive. You can do optimistic like ZK proof verification. But the idea is this is that like okay, let me kind of talk about what optimistic ZK verification means. But basically, this is that now if you want to do the entire ZKP verification on Bitcoin, there's still a cost for that. Like you would still probably I would say about $1,000 in US dollar to kind of do the proof verification. There is another way to do that, is that like, okay, let me just post the proof. And if in the next like 5 block or 6 block, someone see that this and say that like this proof doesn't look right, I want to like kind of show that it's wrong so that like I can kind of like just like, I would say it's a little bit more like for proof is that you post a proof, and if 6 blocks later nobody can challenge that, then I assume that this proof is correct. And this is not really a new idea because in Lightning Network, you rely heavily on watchtower who can see transaction on mainnet, and if something actually is wrong, watchtower are responsible and they need to act fast enough to help say that like, that transaction is not right, let me prove that it's wrong. So we can also do something similar here, is that I will post a proof verification, and if nobody is going to challenge that proof within like a certain period of the time, we will assume that this is correct. But because it's on Bitcoin, so everyone can see it, and you only need to require like global watchtower. OpCat can give you that, and this have a few benefits. First of all, with OpCat, it will be much simpler to than like BVM to do the for proof. It's 0 round, like it will be very easy. Basically, you post the proof and you just wait, sit back, and relax at home. Like some verifier will figure out how to deal with it. And if the proof is valid, there's basically no cost at all to do this. Like you post the proof, nothing will happen because it's not challengeable, because it's correct. Then you can just move forward with that. Okay, now I will talk about why you cannot easily do that with OpCat. The problem is this, is that if you don't have OpCat, I think actually the bigger problem is that if you want to do general purpose computation, like for example using BVM, data availability is going to be a big problem. So in BVM, you need to make data availability, and they also need to be done in a very specific way so that they are what I call challengeable. That's that if the data you post here is being shown to be not correct or inconsistent later on, I can slash the operator. And the problem here is that like if you want to make like data availability that is changeable, we only know one way to do that. That way is like this, that first of all, you need to commit the data, and the only way that we know how to do that at this moment is to use like Lamport signature or Winterny signature. That have a cost. Like and also is that okay, this is a cost, but that like you cannot commit too much data using that because you will need to post that data elsewhere. So people usually will also use like Merkle tree or something, or like just use hash function to compress the data. But you basically need to do these two things in order to commit the data. And the problem with that is that this will be very heavy, especially in BVM, is that like, so in BVM, this is also an issue, is that if you ask the operator to provide all the data, this can be actually extremely heavy. That might actually ruin the benefit of BVM. So in BVM, what it says is that, okay, we will do this, but only on demand, is that if someone challenges that, I will post the data. And this person who challenged me will need to pay for the data publication fee. And that's not the idea in BPM. So this is like, but what I want to say is that without OpCat, you actually don't have a lot of the way to do like challengeable data availability, and every bit will be very expensive. And that and this is like even worse for like Start compared to ROS 16. Start need to post a lot of data, so that it will actually require much more DA for that. BBM now, they actually have a progress. I will not be the person to talk about that. Like some other company will probably talk about that like in the incoming months. But basically that like that is a way to do BBM DA more efficiently. But that like Start still suffer from that. Is that Start still will suffer from like the difficulty of DA without OpCat, but it's now possible. So Start will and us are kind of also working on like a BBM version of the Start verifier. Okay, but that like another company will probably present how they do like this like bone trick on like DA like later on. Okay, but with OpCat is easy. Just create a Merkle tree and show people the root of the Merkle tree. That kind of complete the data availability. Basically, that you have a script. In this script, you just write out the data, and then you hash everything together and say that, okay, I publish all of this in a transaction so people know that. And this is challengeable because you post that, you can put that on the state, and people later will challenge directly on the state. The key part about this is what OpCat enable is that just by writing data on the like blockchain, because there is recursive covenant, you can challenge that. Basically, that it makes challengeable very easy because you can always look back into the history of the blockchain, while BBM itself cannot use that because you don't have OpCat. And another problem about why, so this actually come back to the title is that, well, without OpCat, why would that be very difficult is that now Merkle tree also become much more expensive because you need to manually evaluate hash function. And that like the best result we know at this moment for manual evaluation for hash function is probably like 75,000 script bytes for hashing like 64 bytes. And that's from like Blade 3. And another limitation with our OpCat to do this general purpose computation is that like it's not easy to parsing data. Like in BigBM, you probably know that the execution will be split into a lot of the chunks. The problem is that if you want to pass data around this trunk, so with OpCat, you actually have some very interesting design that you can even build key value storage easily. And that like you can actually use that very cheap, so you can just pass the data any way you want. I will show this example later on, but basically that like we can actually write Rust code and that like we can actually abstract this memory primitive and you can use that if you want, like when you are writing the script. But if you don't have OpCat, you can still do that. It will be very heavy. You will need to use Lamport signature and Winternis signature to do that. And you also need to use manual hash function as I mentioned before. So this is kind of the problem that like without OpCat, yeah, you can still do all of this, but it will be very like complicated. Okay, I will end this call by just giving you some of the like highlight about like our increment the start proof verifier. But like a large part of this will be about our like domain specific language on how to write that start proof verifier. So you can also do that your own. Okay, we do like a Rust-based like DSL. Like in Stack, you will actually touch a few of the like what we call like data structure or like few element. You can actually just define them as regular Rust like structure, and you can build that like step by step. Like for example, in start proof verification, we have something called M31. It's basically a number in the finite field by a prime number. You define that, and when you are going to do the like few extension of the element, you can also easily build that just using Rust to do the like composability. You can create what we call the complex extension of M31 by just have like the M31 element as one of the like struct, and you can basically use that to construct the complex extension. You can do the degree 4 extension by extending from like the complex extension. This allows you to represent the data like that is like in a way that is like composable. And that, like if you want to do addition, like when we want to write the script to do finite field addition in Rust, what we do is this, is that you write a more complicated version for M31. Later, when you are doing the complex version and also the degree 4 extension, you can just build over that. Like for example, here I write the code. It's actually also not a lot. But when you are doing the complex extension, you will just say that, okay, how do I do the addition? The imaginary part will be added by the imaginary part. The real part will be added by the real part. Okay, that complete the complex extension addition. Degree 4 extension is done by adding the first part with the first part, second part with the second part. So I can also similarly implement that. This allows you to reuse as much code as possible, and you can build up the basically complicated function from smaller function. And all this is done by using Rust. You don't need to write a separate compiler. They are actually just like a wrapper using over Rust. Okay, and when we want to finally get the script of the program that we write in DSL, it's actually quite easy. Like in the previous code, actually there's something called CS. And the operation that you've done, for example, here when you insert the script, CS will actually store the script information. And at the end, you just use the compiler to run over that script. You will get a structure, what we call compile program. And inside it, that is the script. And that will be the Bitcoin script. So basically that this DSL allow you to write the entire program almost entirely in high-level language. And eventually you compile it give you a Bitcoin script for the entire thing. Okay, and you can actually use this to write high-level code very easily. Like for example, here is one specific stack on the start proof verification. On the right is what actually happened. What do you want from it? And the left is basically the code. And actually this can be written even easily. Like for example, I can merge the line with the div to the next line. But this is how easy it would be for you to write the code. You can write it almost like you are writing regular Rust code. And another example, this one is a little bit more complicated, but as you can see from the right, that's the code that's actually being executed. The Rust code where I would say is clearly not entirely the same with you write the Rust code directly, but you can say that it's become much more human readable, and you actually see no Bitcoin opcode here. And this code will actually be the compiler will actually generate a very comprehensive script that have to do all the operation. And that will also build a database abstraction that I showed previously. You can here is basically the code where you want to compute some coefficient. What you do is that you read the data from here is basically memory, and then you finish the computation, you write them back. And this number that I read from the memory is done from previous execution. And after my execution, I have the data. They will be written and they will be used for future execution. And the only additional step that you need to do for using this memory abstraction is that you need to initialize that. When you have your script, you initialize that at the beginning, and you have save the memory at the end. And you only need a final step to do what we call memory checking. You only need to do that once. Okay, and I will end this talk by just showing you what is the transaction or the workflow of our start verifier. I'm not going to explain each part of it, but the script will be actually split into a lot of the smaller chunk of the will be split into a lot of the small chunk. Actually, each of the chunk will be pretty small. None of them is I think none of them is larger than 100,000 bytes. We just want to make sure that it doesn't impact the blockchain as much, and we want to make it easier to design. It will run a few steps to do some computation, and then it will go to what I would say a circle. That you were doing the A transaction inside this circle 8 times, and finally it will go to the cleanup. And after cleanup, you can do other things. You can, for example, because you have the slide, you want to use that, right? For a roll-up, the anything else will be the one that settle layer 1, layer 2 token exchange or something. And you can also start a new proof, just verify the next proof, from here. But this is basically the steps. And you can find the code for each of these steps together. But we can split the script. And here, actually, we split that manually. You split that based on the meaning of that step. You don't have to really figure out that, okay, I'll automatically generate that. It's actually also easy for you to just split the step based on that utility. Okay, and that's basically the code for it. And this actually kind of involves some detail about how the proof system actually work, but that like you can always find them on the code. Yeah. You have a question, right?
Yeah, I can wait till that.
Okay. Anyway, like the end is very quick. So we have the GitHub repo, and we also have a Telegram group that if you are interested, you can join. Yeah. I think if you have a question, I need to give you the microphone, right?
Great. Thanks so much for the talk. This is a bit more basic. It's about on the Bitcoin side and getting the transactions included in blocks. And basically, I'm curious, like, because I think in a previous talk you had to deal with constraints on in the mempool, like the limits on ancestors and descendants and the size per block. So I'm wondering how, if you're working around that, how you're doing that.
Oh, this one actually still suffer from like the same limitation. But the solution for that is like this. So what would be the like that's so this actually haven't yet used that technique to bypass the limitation. But the way to bypass it will be like this: is that here I actually kind of submit the transaction kind of sequentially, right? You have the step 1, you have the step 2. You think the step 2 will depend on the step 1 transaction. The way to bypass that is that you run this transaction separately. Is that step 1 will be one transaction. Step 2 will be also an independent transaction that actually have nothing to do with step 1. But step 2 will be basically saying that I claim this to be my previous state and I claim this to be my after state, and will show that like the state transition is correct. And it will actually not track what the like transaction 1 is doing. Like basically that after all these like steps are being completed, and each of them were, how you say that they are logically depending on each other, but they don't depend on each other from the transaction flow. Like they don't consume the previous one's UTXO output. You have the final, basically that after all of this is being executed, you have one single transaction that basically loop back into the blockchain to check that, okay, step 1 is present, step 2 is present, and the step 2's like input match the step 1's output. Basically that you would defer to the final stage when all of them are being settled, and then you start to tracking that. The benefit of that is that because the mempool is not aware of that connection, they will treat them as independent like transaction, and therefore the descendant and ancestor limit will not apply to them.
Got it. Thank you.
Yeah. Let me pass by the mic. Yeah. Sorry. Okay.
Thank you. Just a kind of question on your personal perspective on OpCat and like, is it going to happen? When it might happen? I mean, as someone who's spending a significant amount of time in research in this area, how do you kind of evaluate that? You know, the risks involved in that, and yeah, how do you kind of what's just sort of your personal perspective on it?
Yeah.
Thank you.
So first of all, like the risk for me is actually kind of not too much. Why? Because like Star will give us a grant, so that like it's not like, oh, if OpCat eventually didn't move forward, I am wasting all my time. I think like so far based on basically I talked with like some like people, some of the core developer. I think what happened with like Bitcoin history is like this: that we have two like big changes to the protocol, right? Segway and also like Taproot. Both of them have a little bit of their own unique history. So I think it's a little, I would say OpCat is, wait, only 2 minutes. Okay, OpCat is a little bit like this, is that like, if someone push for that, and that a lot of the core developers start to review that, it might actually happen very quickly. So I would say that there is no set timeline, just need people to add on that. Because one thing that was actually show up in a like informal discussion yesterday is that, oh, did we already submit a PR for merging OpCat to like Bitcoin, basically the like Bitcoin core? Actually, yes, it was several months ago. People forgot about that. You can actually ask the core people to probably can be done in 1 day or 2. Like what is like really missing at this moment is that like what is the strong incentive to do that today? It's a little bit like something you can always procrastinate. And that like Bitcoin history, if you look at Segway and look at Taproot, they are also kind of like they, as I say, is that they still have their own history of how it eventually happened. OpCat probably will not follow the same way. But that like, I personally think is that like, this is probably not harder than with dog. Yeah.
Do you think that it might be easier to activate FCAT on another chain that is like derived from Bitcoin, like or something similar? Like in some ways, Signet for the Inquisition serves that, but there's no like real assets there, so you may not get like the similar incentive to kind of vet out that like these. This actually like proves out while we are waiting for like core devs to approve it.
Yeah, I guess I might be running out of time, but I think so. Signet already have that. Fractal is also a Bitcoin fork that kind of try to do that. I think really the main thing is that like, well, why do we do that on Bitcoin? Have a lot to do with like Bitcoin itself. I think it's not just the chain; it's more about like the token value and a lot of that. Is that Bitcoin is still, you think about that, Bitcoin is the biggest asset like in the like blockchain ecosystem. And people think you can actually build a lot of the application over there. This is actually kind of similar to the question is that why it didn't have all those things, right? They can also be done on a different chain. So my perspective, and I think it's a reason why a lot of people, even a lot of the investors, they really like Bitcoin is that if you look at just this like macro like data, like, okay, how much is the Bitcoin total valuation? How does the Bitcoin performance throughout the year? Is it a lot of speculation or they actually have a stronger support? Bitcoin is like more positive on that side. So kind of like, it's kind of like people thinking that like Bitcoin seems really good from different perspectives, including the token. And that like we can do, basically if you want to build something, Bitcoin might be a better like ecosystem for you to do that. Yeah. Okay, I think we need to do the next, like it's the next talk, right?
Yeah.
Okay.
Thank you.
Thank you.
All right. So I don't know if we mentioned, but Robert could not make it, so he sent a recorded video that he made this morning. I'm going to try to figure out how to best run the video at the same time as broadcasting the live stream from my computer. This may require a little bit of deft configuration. We will see. Okay, so that presentation view works. Yeah, so, yeah. I'm going to say, okay. The main issue is that I have an audio routing problem. I think what I'm going to do is we're not going to broadcast the video onto the stream, and the stream is just going to go to a background loop, and I'm going to play the video from Robert.